Hello? Well, at least there's a lot of people there.
Yeah. Not a lot of talking though.
Yo, lousy. Interesting.
Yeah. I don't think this is working out, man.
Lousy. Hee-haw. Alright, let's learn about veganism.
makes me so special?
He was waiting for you. He said, I can't go in there until you undeafen. And then he's now in here.
Oh, God. Here we go.
Yeah, we can hear you, Jesse.
You're coming through loud and clear.
Go on, Indio's undeafen now.
I laced up my boots.
And by the way, that was a hell of a feast.
Yes, sir. I'm here. Oh, I feel better. Thank you.
So why did you cherry pick your data?
Well, I don't believe I did. Would you like to point something out that you think I cherry picked?
You think that how many data points do you have? Like 20?
In which one?
Your dip spreadsheet.
The one that shows the curve, or the one that shows the same location?
Your spreadsheet with dip angle.
Okay, let me look. I don't remember the exact.
Because you didn't do all those, right?
No, I did most of them, but I had contributors from some other countries and some other states, including 2 flat earthers.
Yeah. So why did you choose those? Is that it? Is that all the dip angle measurements that exist?
No, but it's the ones I got my hands on.
Well, I mean, you could have used George Hottenuke's ones, right? The frozen lake he did.
I don't remember seeing angles for those. I can put them in there if you like.
Well, his shit's all over the place. That's what I'm saying. I know for a fact that there's measurements all over. I know how surveying works, and I know that they take. I actually watch them outside my building all the time because they're constructing a building right next to mine, and they measure the corners to make sure that the building isn't sinking. They sit out there all day taking measurements. And why would they do that? Why do they prescribe doing measurements at certain times versus other times, or in certain weather conditions?
They're trying to reduce inaccuracies because they're shooting for a very high level of accuracy.
Okay. You're not?
Well, I'm doing the best I can. But I'm well aware of the fact that I'm not going to get 1 millimeter accuracy at 75 miles, right?
You're not going to get any accuracy.
So, do you know that there's a difference between a device that says it can measure some angle and what it can actually measure? So there's like the internal angle, there's the precision of the device itself within itself. So say I have a physical protractor, right, with gradations on it. And I know that I can turn my theodolite. Now let's imagine it's an old theodolite with a physical angle measurement, and I turn it. Now there's the precision of the instrument itself, right?
Right.
And then there's the precision of the optic, of doing the measurements through the optic and how those are correlated. When the theodolite says we can measure an angle of 0.05 arc seconds, they're talking about the instrument. They're not talking about the actual measurement.
Right. They're talking about the measurement of the angle of the light.
No. They're talking about the instrument itself.
But don't they list the accuracy for the entire instrument?
How would they measure that? How would they verify that?
You can't verify it.
So say I want to, what is my accuracy at 100 meters? How would I know? How am I going to test that? Am I going to set up an optical path with a bunch of mirrors, try and test it? What about 1,000 meters? What about 10,000 meters? What about 100,000 meters? How am I going to actually test that? How am I going to calibrate my device? Yeah, so when they're talking about precision, they're talking about the physical instrument.
Yeah.
Like a ruler has a precision, right? A micrometer, a calipers, they have a precision. But this is, at some level, it's optical, where you're outside of the instrument, right? So something's happening outside of the instrument.
Okay.
Okay, so that's what I'm talking about. So you have things, and I brought this up to you. Deflection of the vertical. And you sent me a page, right? That page had like 9 different models for deflection of the vertical, and they didn't match each other. Deflection of the vertical is something they came up with because the so-called celestial sphere doesn't align, the astrogeodetic surveying, let's put it that way, doesn't align with the geodetic surveying. So they have to have something, they've known this since the 1400s, they have to have something to fix this discrepancy.
So are you saying that whatever you call it, deviation from the vertical, is a likely cause for my measurement that plots out as a curve?
No, the truth is you didn't have a measurement. Not really.
Well, I mean, all measurements of non-integer type have some margin of error, so it's not that I didn't have a measurement, but that you may argue that I had a margin of error that was too large, was larger than the value I was trying to measure.
Well, you know, when we're trying to get...
There's 2 things, though. There's also the uncertainty. The uncertainty of the accuracy of your measurement in the first place.
And
there's precision, and then there's uncertainty.
Correct.
They're 2 different things.
Correct. Do you have some evidence that my uncertainty was larger than the what I'm calling the missing height?
Do you have evidence that you allocated for your uncertainty?
Well,
we can't know what your uncertainty was because we have 1 data point.
Well, but I have a bunch of data points, and they sort of plot a curve. And if my uncertainty had been of a random,
what about all the data points that don't plot a curve?
Literally circular logic.
Right. Well, what about all the data points that don't plot a curve?
Yeah. So
why'd you leave all those out?
I didn't.
Well, you only selected the stuff that matched your conclusion.
Look, I doubt you took 1 measurement per observation and then wrote it down and then stuck it on your spreadsheet. You didn't do that. We know you didn't do that. You didn't take an average. You didn't take a weighted mean. You didn't take a mean. You didn't do anything. You cherry picked your shit. Okay? It's obvious.
No, and actually, in some at one of the shots, I took several and I put several in there, and they're slightly different.
Well, I mean, that should tell you right there.
It's slightly different.
What should it tell me?
It should tell you that there's variables you don't even know about.
Absolutely.
Okay.
So let me go this. Is refraction the same when you're looking up versus when you're looking down?
Just keep talking, Jeff.
If you're looking at it to a point at a higher elevation versus to a lower elevation.
I would say if your line of sight goes through a stronger density gradient, which does tend to be closer to the surface, then you would have more refraction if your line of sight is close to the ground or the water than if you're looking up.
Density gradient.
So, okay, there is something that's called unequal refraction error. So when you're going up a slope versus when you're down a slope, the so-called refraction error is different.
Okay.
Okay, so if you're looking up versus whether you're looking down, right? So some of your measurements, they're looking up and some of them are looking down. Right? So all these are all sources of error, which is why I say you're cherry picking, because your numbers are too clean.
How do you, I mean, by what standard do you judge that?
By the fact that there's a large, I just told you why. I just gave you one example, is that you're looking up versus when you're looking down. You're going to get a difference, right? So if you do a whole bunch of observations looking down, you're going to get one sort of refraction error, and then you're going to get a different value than when you're looking up. But the thing is, yours all match 1.
But they're not all looking up or all looking down.
I know. That's the point. Maybe you don't get it. Your so-called error matches 7.6R, right?
Pretty close, yeah.
Yeah, pretty close. But it's not a universal error. It depends on which way you're looking. The 7.6R is for horizontal measurements.
Hey, hold on just a second. A
Okay.
customer is calling me.
Literally saved by the bell. Wow.
Oh,
I like where it's going.
I'm about to dig deeper.
Okay.
Yeah. I don't want to give much of a commentary whilst he's still here.
I mean,
Is what he's done measuring the dip by leveling the theodolite?
yeah.
I mean, the operational range of level.
Yeah, I mean, we didn't even get into that, right?
That's what I've been saying. He was and I'll just wait because Indio's got a good point, but yeah, he's way out of.
I'm gonna let Indio do
and the
his
thing
point.
is, small errors, small angle errors, like they're great, like the calculation, right? So if I have a small angle error at 10 feet versus 100 miles, it's a huge difference, right? Because that error gets larger.
All right, Jesse's back, India.
Yep.
Where were we? Oh yeah. So what if you were in Europe or Finland or Massachusetts? You know that they don't use 7.6R in Europe. They use 0.13, and in Massachusetts they use 0.17. And then you could just go like the Department of Transportation, right? Every state has a Department of Transportation, and every state has a surveying manual, and every state uses a different so-called refraction correction. Did you know any of this?
No, I'm not even sure I know what that means.
7.6R is a refraction correction of 0.16.
Standard terrestrial refraction, right, Indigo?
Yeah, the so-called standard.
So that's
in Europe they use 0.13, and they've been using that. But if you go to like Finland, they use something like what the hell was it? Let me think for a second. It's some huge number or something. It's like 0.19 or something. And then if you go to like here's the funny thing is, it's like kind of correlated to so-called latitude. So the closer to the so-called equator you get, the less of a refraction error that they use in their calculations for surveying. And you're in Canada, right?
No, I'm across the Straits of Juan de Fuca from Canada, but I'm in Washington.
Well, I mean, so what's the refraction error they use in that state?
I don't know. I just looked it up on Wikipedia, and it said it was basically 1 degree for every 932 miles.
1 degree for every 932 miles?
Yeah, approximately.
I don't even know what that means.
Well, that means that if for every 932 miles, something will appear 1 degree higher than it otherwise would, allegedly due to standard atmospheric refraction.
Yeah, due to magic.
Sorry, this is standard atmospheric refraction. Indio's just pointed out that there's not really a standard. Yeah, there's no standard, depending on the politics of the country that you're in, or the manuals, at least, of different countries and at least states within the USA. You will have a different standard refraction calculation. Oh, it seems to. It is. I mean, is that new knowledge to you? Have you just come across that knowledge? Right? Is this the first time you've heard about that?
No, I mean, I've seen different representations of the same thing. Some people write it as 7/6R. Others write it as like this K factor of some fractional decimal number or something.
Yeah.
There's different ways to mathematically express the same curve of light.
I need to ask you: is that an optical or mathematical function?
Well, I mean, the mathematical part is mathematical, but it's alleged to describe an optical phenomena, right?
Alleged. Okay. Is it optical or is it mathematical? It can't be optical.
I think it's an attempt to mathematically model.
Explain why you see too far.
An optical phenomena.
So math is a language. It's explaining why you see too far.
It's not bending light, is it? No matter what the terrestrial refraction is, it's making the geometric shape mathematically bigger.
Yeah.
Right?
Yeah, but
yes, that is what it's doing.
Hey, Jesse, look in Livestream voice text. I want to show you something. This is what you think you're doing. This is what you think is happening. That you're on a ball and you're looking and making measurements on a curved path of light.
Basically, except you're showing refraction a rate that far exceeds what is said to be standard refraction.
No. 76R means the radius, that if the ray of light was a circle, it would have a radius greater than the radius of the Earth.
Which means you could zoom in on your own ass. Theoretically.
So 76R, 76 the radius. R means radius. That means that path of light. So what they do is this circular light path. But it's a cheap and dirty way of just saying, we're going to assume the globe is 76 the official radius. And then we're going to model it as straight rays of light.
What is it when you don't have evidence and so you create a story to fill in the gap?
Lying?
Oh.
That's what globers do, okay?
Yes.
But
do you know what the operational range of like a transit or a theodolite is? Like if you're trying to be accurate? Like let's say I'm going to put down a foundation and I need 1/32. I'll make a big flaw here. 1/32 of an inch.
If you're trying to pull 1/32 of an inch accuracy, you probably want to keep it under 50 meters.
It's about 550 feet. 550 feet. You know why that is?
Why is that?
Well, what's the frame of reference for level on a theodolite?
Bubble levels and or the built-in electro-optical compensator level.
Well, the problem with those is it's the same problem, is they're only a 4 or 5 inches wide, right? What are they leveling? They're leveling the machine itself.
What's 4 or 5 inches wide?
The theodolite.
Oh,
where the level is rigidly attached is what you're going to be measuring as being level.
So why do they make levels of different sizes? Why do they have like a torpedo level and like a 4-foot level and like a 10-foot level? And that if you use those to level something, you get different results.
Yes.
So in a theodolite's little bubble level, it has a diameter of like, I don't even know what, a thumbnail.
So
what I'm saying is the level, right? So you did an observation that was 120 miles, right? Or somebody did. It's in your spreadsheet.
No, 105.
Okay, so someone did 120. It's the last one.
What?
The Mount Shasta to, I can't remember what the other one was.
Mount Scott. And no, it's 105 and I did it.
Oh, 105. Okay. So you think your theodolite, set it up, put the bubble level, that if you drew a line, a straight line, a level line, not a curved globe line, a level line, that you could extend that out 105 miles and it would be level all the way there.
Well, level within plus or minus 4 arc seconds.
That's what you think.
That's what the machine's rated at.
That's what the machine.
How far was that? Like, you go ahead, Meme.
All right.
I've been tripping.
Look, if you use a torpedo level, what you're still saying is it's a torpedo level, essentially. Okay. Let's say you have a nice, like 1,000-foot long wall. You take a torpedo level, you draw a line where it's perfectly level. Take a 10-foot level and put it on that mark perfectly. Do you think you're going to still be in level?
Well, I've never tried, but if they were both calibrated highly accurately, and you had them both on the same plane of levelness, then they should be.
No, it's not. And then we have things to prevent that from happening. Torpedo levels are for specific things because they do not have the range of accuracy as a 10-foot level. Doesn't matter how good it is. It's because ultimately the machine itself can only read itself. There's no invisible thing that says its fidelity has been maintained past that point. You may only need a spot where you need a 4-inch level, and that's the only spot you need it at. But the actual equipment itself doesn't have the capabilities of testing whether that line has maintained its fidelity 100 feet away. Whereas a 10-foot level, you've created a much larger margin of error, or a much smaller margin of error, and so you're going to have more fidelity of your line at either end. I mean, this is basic construction, and all of us who build and survey and who do all this kind of work understand this principle pretty easily, because you cannot build things practically. Like, I could not put down, if you gave me a 4-inch level, no foundation would go down.
But let's say we had a perfectly smooth, flat, level plane, and
what are we measuring it with? How do we know it's level?
Let's just say that it's floating on water, and so it's level. And we put a bullet level or a torpedo level on there, and a 8-foot level on there. They should both read level if they're both calibrated correctly, right?
So you're talking about putting them both on something that is already known to be perfectly level.
Yes.
Yeah, so almost like them back at the factory being put on the calibration machines that test them both the same exact way. Because you know the 4-inch level is still tested the same way as the 10-foot level.
Yeah, I've seen the videos.
Right. So, but ultimately you still can't use it when you're free floating, when you're elevating, when you're holding it, when you're putting it up against things, when you're putting it into use for practical purpose. It just doesn't work. Because there is no, ultimately you're relying on the ability of the piece of equipment to internally operate with the assumption that everything is perfect going out from it. I mean, this is how we put down houses, how we put down roads. I mean, we put up 1 million square foot warehouses for the military, and they had stations everywhere and GTR units or GRT units everywhere. And reflectors set up everywhere, all over the place. Because they're just not as accurate as you think. And these are, $130,000 stands that we have, that we use.
Yeah. So the question I got to ask is, when you use a physical level, the mechanism in the level that you use to level is liquid and an air pocket. But the secondary mechanism, which is the effectiveness of the decision of whether it's level or not, is what? Your interpretation of what you're seeing. You decide when the bubble is between the black lines. Right? And everybody knows, who's been on a construction site, that no two men and no two positions relative to the level give you the same reading. So even with the precisely engineered machine, let's say Stabila from Germany, right? One of the most expensive levels you can buy, the man and the situation is going to have error. So even though the device itself is precise, and the forces acting on it allegedly are precise, the interpretation of whether it's level or not is never going to be consistent. So when you go out into the field and you want to level something, anytime it requires a man to make the decision when it's level or not, or when you're targeting the target at level or not, there's going to be error. And everybody knows, who's ever shot a gun, that a small error at the sight picture results in a large error downrange. So anybody who tells me that they did this or that with an optical device The only standard that first must be known is how did you maintain level and maintain your sight picture to validate the claims that you're making. And if you don't have a methodological practice that can result in perfection and negate the error, and you can't explain it, then anything you say after that is a waste of my time.
Well, the instrument is designed that if you follow the procedures, the instructions for operating it, that you will be within the stated accuracy. And besides, the Nikon unit actually has a built-in liquid level where actually they take and bounce a little laser beam off the inside surface of a clear liquid in a quartz vial, and then that beam hits a little CCD imager, and then based on where in the CCD area that laser beam hits, then the computer is the one that actually objectively, reliably, consistently reads the levels. So there's actually no human input in even reading the level on that one.
Right, and that's fine because like we all have those, and the self-leveling levels, the self-leveling transits. How far out have they been tested?
I don't know.
I do not know of a test facility, like a controlled test facility.
I've actually tried to find this out, but there's nothing.
You can't. I already know there is nothing. You can't. The only test they did ever was with mirrors, and then they said there was because of the inaccuracy of the mirrors, they can never remove a margin of error of even testing. So the issue is there's no way to test how accurate that is. That may indeed be really super accurate, but you're still, like, even with the top of the line equipment, your diameter is now what, 900 feet?
I don't understand.
The radius of accuracy. The radius of accuracy is about 900 feet on the most expensive, best transit systems there are.
What do you mean the radius? The distance you can shoot is 900 feet?
No, not shoot. Accurately measure as level.
Oh, meaning that what I think is a straight level projection through the telescope could vary vertically by plus or minus 900 feet?
No. That means that if I send the guy out with the stick, the maximum he can go out is about 900 feet from the transit while I measure. Because after that, error creeps in.
But enough error that, error creeps in at any distance. I mean, even at 10 feet from the front of the device, it's still got an error of plus or minus, say, 4 arc seconds. That's still an error, right?
Okay, if you get that small bit of an error at 9 or 10 feet, 75 miles, 105 miles. And that's if you even know the amount of error you might have. Like I said, they've been trying this with the theodolite, and when they do it, they still can't decide if the horizon is optical or physical. It's optical when it works for them. It's physical when it works for them. You know, they only cherry pick the data, as you have, that supports the initial claim.
So let's say I did get up on Mount Scott, 8,934 feet, and I shoot I shoot an angle to Mount Shasta, 105 miles away at 14,179 feet, and I measure an angle. What's my problem there? Where did I go wrong?
Okay.
Hold on, I'll answer that question real fast.
Well, you go ahead. Sorry. I'm just laughing because I'm thinking about the GIF I posted with the curved lines. Like, you don't even have straight lines to measure an angle. You have two freaking curved lines.
Exactly. Right. Check this out. When you orient your device to the image of the mountain, you are not shooting an angle to the mountain. You're shooting an angle, quote unquote, or orienting the device, quote unquote, to the angle of the incoming light.
Agreed.
So to first say I'm shooting an angle to the mountain, you're already self-defeating. And without the accuracy known, right, and the geometry known and all the factors known, you can't make any conclusive statements.
Well, you're assuming that the angle to the mountain and the angle of the light arriving are different from each other.
If you're on a globe, there is no angle to the mountain.
Yes. Listen, on a globe, it would necessarily not be the correct angle. That's their excuse for why. Listen, hold on, friend. That's their excuse why at 900 miles there's a 1 degree off. Now, the reason why they needed this excuse is because of the Selenelian eclipse defeated their model, and they needed to come up with a reasonable excuse of why these objects where they claim are in a specific point in the sky aren't where they're supposed to be.
So here's what I don't understand is like we have like over 100 data points with all the measurements taken of seeing things that are way too far down on ground level.
But you don't have any where the line of sight doesn't pass close to the surface.
So, are you assuming that there? Are you assuming? Yeah. Are you assuming that there is some kind of unknown effect that is turning the Earth into a hologram?
I don't know about any hologram, but I do know that when light passes near the surface, it tends to bend downward.
Oh, does it? Do we have Gosh, is there
why do you think that?
Some science for that?
Yeah, I want to know why you think that.
Yeah.
Well, because I went out to the beach on a hot, calm day, and I set up my telescope below the top edge of a county park sign, and I waited for a ship to go by out there. And then a ship went by, and I could see the water line on the side of that ship, where the water, meets the side of the ship, over the top of the sign, even though the sign was higher than me and higher than the target. So the sign was objectively, physically between me and the target, and yet I could see the target over the top of the sign.
So what was the elevation of your telescope?
I don't know what the absolute elevation was, but I know it was
8 feet,
like a couple inches below the top of the sign.
So was it 8 feet above sea level, or?
No, it was about 2.5, 3 feet maybe.
2.5 feet. Do you think there's any waves on the ocean?
Not on this day. This was not the ocean. Day. This was the Straits of Juan de Fuca, and there was no waves.
No waves. Salish Sea.
The Salish Sea. Oh, okay. So there's no waves on it. Oh, okay.
But the water does come in and out, right? The water level changes.
Oh yeah.
Yeah.
So you have a surge.
Yeah. And I know where you did the observation, and there's a tight. And if you can look at the currents there, there's a swirl there.
So you think?
And plus, you also said a tendency to bend down. Okay. Your single data point does not show a tendency.
Well, I've got other film from other days showing similar things at the same location.
And we have film of lasers bending into the air, upward.
So about that, it turns out that when the observer is down in a stronger density gradient area looking up to a laser beam that's in a lesser density gradient, the beam appears to be curving up to the observer even if the beam is actually slightly curving down.
How is any of that falsifiable?
Yeah, listen, first of all, that's not the observation. That was done. Like the upward bending lasers, they were done. You can see it going straight and then doing basically a right hook, a J hook straight up into the air. There's a bunch of them. It's not like there's one. There's a few of them. And here's the other thing: is your claim that you can, because light bends down to the density gradient, the lower you are, the more refraction there is.
Well, if being lower makes you closer to a colder water surface that's colder than the air, then that usually does increase the density gradient rate.
So if you've got it...
So hold on, Meme. So the lower I go, the farther I can see. Is that what you're saying? If there's more refraction, the lower I go, that means I should be able to see farther the lower I go.
Not necessarily, because being higher also allows you to see farther.
So where's that transition? Between I can see farther because of refraction and now I can't see farther because of refraction because my closest to the ground overwhelms the refraction. Yeah, it's quite the conundrum, isn't it?
No, but it's simple, and I don't understand why you don't understand it. But
understand what? Listen, I constantly have heard this claim that there's more refraction closer to the ground, that you shouldn't do observations over water. That means that I can see farther the closer I get to the ground. Yeah, it sounds that stupid. That's why you're having a hard time, because it sounds that stupid. And my oven's going off again, so someone please take over.
Where's the paper? Who has the paper on the refraction? Because all of it's done with straight line measurements anyway.
I'm not sure what paper you're referring to.
Okay.
And I'm not even sure why we're talking about refraction, since I made no compensation for refraction in my measurements.
Okay, well, that would mean that you're assuming that the Earth is, like, the horizon of the Earth is geometric and physical, right?
My measurements made no assumption about the horizon. They don't involve the horizon. So I'm not sure I understand the question.
Well, if you haven't accounted for okay, then explain the black swan image where you have a horizon that is 10 miles away.
At least.
Well, I saw the horizon I just told you about over the top of that sign.
Okay.
So
do you know what the black swan is that comes from the ludic fallacy?
Yeah, it means
so the black swan means that it doesn't matter how many white swans you have. That's why it's called a black swan.
But if I were to discover that the black swan were actually a white swan painted black, I found the paint can, I found the brush, I found the guy who says, yeah, I painted it, then I've kind of invalidated the black swan, right?
Well, no, you haven't, because the guy goes down there every day, all the time, and gets these images.
Actually, the BMLS 69 guy said in his video that he went to the same spot as many times as he could, like in a 3-month period, and that most of the time the 3 oil platforms appeared sunk down as if the Earth was a globe, but a few times they were all risen up and all visible as if the Earth was flat.
Okay. Let me ask you this. Let's say you're looking along the deck of the water, right? And water is reflective, and you're at a very low angle, aren't you? Right?
What's the deck of the water? Just like if I'm down by the water?
Yeah, I'm calling it the deck because that's the flat portion that we're talking about, right?
Oh, okay.
Okay, so the water is a deck, right? So what happens when you lay down? Does the water look like water, or does it turn into a mirror? Comes a homogeneous reflector.
It depends if it's hotter than the air. If it's hotter than the air...
It doesn't have to do with heat, it's the angle. The tighter the angle at one end, the more reflective and homogeneous it gets, because the eye can no longer resolve it. It's angular resolution.
That's not been my experience.
Hold on, friend. It's not just angular resolution. It's the internal reflection angles. Once you have total internal reflection, then the angles of light that are not the water, like not the source color of the water, will overtake them from the angles of propagation to the angles of reception, and you'll only see light that is not originating from the water surface. It's just reflected light. If that makes sense to you.
Right. Now, see, someone posted the image of the sunken oil rig. You see it?
Oh, hold on. Yes.
Right. Is that the horizon?
What's the horizon?
By which definition?
Yeah.
Yours.
I mean, technically, the definition of the horizon is where the sky and the water appear to meet, right?
Appear. So it is. It's optical. It's not physical.
Right.
Okay. So none of your pictures or observations are of the horizon. Then they're just optical. Right. None of them are actual measurements.
Well,
I'm not sure what they...
Sorry, none of them are of the geometric horizon. The curvature of the Earth that should be physically getting in the way of stuff. All horizons are indeed optical, aren't they?
Jesse, the point of that is that the apparent location in your field of view, and I want to make that clear, it's in your field of view. It doesn't actually exist down in three-dimensional space. It only exists in the image presently.
You mean like
where
when
the color field, where the color field of the sky meets the color field of the ground or the water, and they distinguish and change. That demarcation point is known as the horizon. That of a necessity cannot be a physical location. So in other words, when you point something at the horizon, you're pointing it at an image. You're not pointing it at a physical location.
Absolutely. But I don't see what that's got to do with my measurements of Mount Shasta at 105 miles because I didn't utilize the horizon.
Because you don't have a measurement and you don't have the fidelity of a level line at 105 miles, and you couldn't be shooting along a straight line. If you're on a globe, you're shooting at a curve. Curved light coming in.
Well, let's just say for the sake of discussion that I'm not on a globe and I'm on a flat Earth, and I'm still on the same mountain, shooting to a line to the same mountain, the same Mount Shasta.
Is this your picture down here?
Let me look. That's my picture, but that's not Mount Shasta.
Okay.
I have a picture of the Mount Shasta one if you like, though.
Well, what's this one right here?
The one that Jace Isle,
Jace AI.
Posted?
Yeah.
That is one of the ones from the data, the chart that shows the curve.
That shows the curve? Where at? Is it behind the hill?
Is what behind the hill? The mountain
is the curve? No, is the curve behind the hill? Because I see a hill and I see a mountain obstructed by a hill.
I just measured the zenith angle to the top of that mountain. I'm not sure I understand what you're asking.
You don't have an angle. It's curved. It's curved observation.
Well, I measured the angle of the light entering the telescope, right?
Right. It doesn't matter. You're saying, okay, let's just say you're saying you're level to that mountain. You're shooting level to it?
No,
okay, you're shooting the angle from down to up. Okay.
Holy crap, dude.
So what? So you think that hill is Earth curve?
The tree-lined hill?
Like if a truck drove in front of you, would that be Earth curve? Because that's a hill obstructing your view.
No, never mind. The hill has nothing to do with anything.
Okay, so where's the Earth curve at?
Well, this is just a single data
point. Hold on, Jesse. Hold on. We got to correct an error on the table. So he asked you something about the angle, and you said, I'm measuring the angle of the light entering the telescope. Now, if you concede that you don't know the path of light from the target object all the way to the telescope, then the angle that the light enters the telescope is irrelevant. And making any assertion based on that is also irrelevant. Can't be applied to anything.
I wonder, is this supposed to show obstruction of the bottom of a mountain?
No. This was just he asked for my source data, and when I go out shooting angles, I line up the telescope to the target. I take a picture through the telescope, then I take a picture of the LCD readout. Then I flip the telescope around. You know how you do 2 readings with a theodolite, at least 2. And take another picture through the telescope, and then another picture of the LCD. It's just my way of recording what I was shooting and what the angles were, because that way I don't have to ask myself later if I maybe transpose some numbers.
Hold on. Let's reiterate this, because this is what the crux of the issue is about. The angles of what?
The light as it enters the telescope.
Right. And unless you know the path to the target object, those angles are pointless to know. You cannot discern anything about the target object's angles of propagation from the angles of reception. Because according to the globe model, all the light is taking curvilinear omnidirectional paths.
Yeah.
And so you have no idea which light you've received. So you can't make any definitive claims about the physical location of an object compared to you angularly based on angles of intercepted light. It doesn't work. Can't be done.
Which makes the model unfalsifiable, which means we can dismiss it out of hand.
Correct, which, by the way, the U.S. military validated when they attempted to shoot a tri-band laser to determine the refractive conditions over 120 kilometers for the purpose of perfecting their laser targeting systems. And they found that the results were not congruent with the globe model of refraction. In other words, it was a chaos. It was chaos. The general consensus, right? Not that they use this word, this is my word, but they use turbulent and unknowable. The general consensus is that the path of light is chaos. And the final point that you're getting, right, based on what they said in relation to the globe model, is not precise, and it's not congruent with any standard model of refraction.
I'd like to point out also, Jesse, that Drace very politely has posted the source and the citation. The combat experiment does not observe dispersion, even though they should have. They say they should have. They use 3 frequencies. It's irrelevant what the purpose of the experiment. There we go.
Let me take a look.
Yep. Yeah, but here's the problem. Okay, and this is the problem since day one. And I mean day one is in the first retard that went out to the ocean and looked out and said, I can't see the bottom of the boat. And because I'm so closed-minded and ignorant about the nature and physics of light in relation to geometry and all of that, I'm just going to assume, based on childhood permanency bias that you learn when your mother first puts a ball behind her back and you realize that the ball continues in 3-dimensional space and doesn't just disappear. You look out and you say, well, I can't see the bottom of the boat, therefore it continues in 3-dimensional space. And just like a ball going behind my mother's back, the boat is going over Mother Earth. Right? Because they can't think of... Go ahead.
Isn't it much simpler?
Probably.
Yes.
Ask them what refraction is.
We were about to dock at that port.
Okay. Sorry to interrupt. That I just kill it quick. So define refraction. Right. That's go ahead. Sorry,
Jesse. You want to define refraction for us?
Oh, by the way, I'm not going to. I didn't claim it.
You're not Jesse.
You're not Jesse.
I just want to invite everyone to the friggin' decimation and annihilation of the thinking atheist, Forrest Gump Velkai, and brain sick, booger eating, the brain sick, booger eating Bubba gets the Gibbon annihilated today at 5:30 on the Quantum Race.
Is there such thing as a thinking atheist? Okay.
Yeah, I was going to say that's a contradiction. What are you doing?
Yeah.
Yeah, I know.
Oxymoron.
I will bring that up. Thanks, Indio.
That is an ox and a moron.
I've been around.
We'll be around more often.
Well, I seen you in here last night, but I was busy. We're like ships passing in the night, so I've seen you around.
I got you.
We're just trying to avoid you.
Do I still have what?
Do you still have your contradictionary?
Oh, yeah. I'm using it today. I also have my hip waders going on. So,
what about the turkey?
Short and
not done yet.
No,
it's getting hot though. It's getting hot though. We're testing the heat of the density of the air above its refracted surface right now.
Too funny, man.
Yeah, I'm gonna post an announcement for your stream, and I usually post them when I see them. When I see you post, so
Oh, appreciate it, man.
In our announcements, yeah. So I'll do it again. I want to see what a thinking atheist looks like. It's like
I'll come and
it's like a cool
hang
unicorn
out
or something.
It might be illuminating.
I'll be there, Kiwi.
Sweet.
Is that refracted illumination?
Yes.
I don't think refraction comes up in this. Thank the Lord. That's all right. They got enough problems.
I don't know. I generally concede to refraction, as you are well aware. So when you apply any of the refracted models to any observation, the first order of business.
Models now. This is pretty funny.
No. Come on. Let me go.
Come on. You sound like Anthony Riley.
Listen, I have a long history of being absolutely two-sided and coming in with a knife in the side while you miss it.
All right, fair enough. But that's not my way, but doesn't mean it's not the right way. Go ahead and allow them to beg the question till the cows come home. Go ahead.
This is the way.
Okay, so when you apply a refracted model, right, because you're applying it to an observation, right? So you have a geometry in your mind of what the Earth is. You then have an observation that doesn't fit that geometry. And so what you do is you break the Earth geometry. And refraction actually means broken over the back. And so I agree that their model is indeed refracted. And therefore I concede, yes, your model is broken. I rest my case.
How you like that, Kiwi?
It doesn't do it for me.
A little too intellectual, I know.
A little too
well, look, it wasn't. Look, it wasn't as delicious as we did it last time because somebody was talking about the mountain, and then we made a pun on Brokeback Mountain with refraction, and then we basically said your argument is gay.
Yeah. I mean, Jesse, what is refraction?
The redirection of a wave due to changes or boundaries or gradients of density.
But boundaries?
Incorrect. Citation, please. That's not Snell's law.
Yeah,
well, Snell's law is for boundaries, right?
Snell's law is the law of refraction.
But how do you apply that?
No buts. There's no buts. None.
I'm here.
No but.
Was that self-deprecating?
Maybe.
All right. The point is there any... What is the assertion of terrestrial refraction? What do you assert that it is?
Standard terrestrial refraction?
Yeah. Not calculate it, what it is.
Say that again?
Not how to calculate it, but what it is.
Jesse, phone a friend. I'll go for you. Trust me.
Ha ha ha. What's your number? Well, I didn't come up with it. I'm not sure. The mainstream model claims that it's the bending of light.
That's not a model.
Well, what would you like to call it?
That's not a model. A mainstream, where is that? Citation, please.
The claim?
Yeah.
Look, they're asking me about something I didn't come up with, okay? I'm not sure what you want me to say.
I thought you were a proponent of refraction. You don't know what it is. Define refraction. Citation. Not you. I want a citation that defines refraction.
You mean like Andrew Thomas Young or something?
It's up to you. Whatever you want.
That'll work for me.
Hold on.
In fact, yeah, that'd be fine. It's my favorite one. You'll find an interesting part in his paper where he said things that will never reappear that are already physically obstructed. So it's a one-way mirror.
So Drace is already over my stuff, man. You're not posting it. I got where you're going with that, but you're a little bit ahead of the game. We just want to know what refraction is.
Well, I've read that paper like 20 times, so.
All right.
Yes.
Let's do this. Let's make it fucking easy.
Okay.
There it is. From Britannica.com. Snell's law in optics, a relationship between the path taken by a ray of light. Oh, by the way, rays of light don't exist. In crossing the boundary or surface. Do gases have surfaces? No.
But they would have a boundary with water.
Of separation between two contacting substances. Where's the two contacting substances in the fairy tale atmosphere? There isn't any. It's a category error. From the physics classroom, refraction is the bending of the path of light wave. Light's not a wave. As it passes from one material to another material. Can you show me two different materials in the fairy tale atmosphere? You can't. The refraction occurs at the boundary. Where's a boundary in the fairy tale atmosphere? There is none. You're fucking category error. Let's go to Wiki. Snell's law, also known as Snell-Descartes law, and the law of refraction, you see the context, is the formula used to describe the relationship between the angles of incidence and refraction. When referring to light or other waves, light's not a wave, passing through a boundary between two different isotropic media, as such as water, glass, or air. Has a picture right down here on the bottom. You see that? Snell's law? Where's the interface in the atmosphere?
Are you denying gradient refraction?
That isn't fucking refraction.
Okay, so when...
Okay, can you fucking... Do you have textual pareidolia?
Hold on.
Do you have textual pareidolia? Do you want me to read them again? Where's fucking gradient in anything that I read?
Oh, I didn't see it in what you read, but I think what you posted was not all of...
You're making it up!
Yeah, what is it? What is terrestrial refraction? Is it just make-believe?
I mean, obviously the phenomena is real because...
It's not obviously real because I look out and I just see things. I don't have to come up with a reason for why I see them. If you're having to come up for a reason why you would see things, that's not scientific, is it?
Okay, so...
Yes, but hold on, Jesse, before you go, because you said this twice and you haven't been corrected yet. So, a phenomenon, to be genuine, the premises of the differentiation in the happening must be known in the first instance. So, in other words, if you see something where it shouldn't be on a quote-unquote globe, in order for that proposition to be true, the globe must be proven in the first instance. You can't infer it and say, oh, that isn't where it's supposed to be on a globe, therefore it's a phenomenon. So, again, where's the globe being proven in the first instance so you could apply this claim of a phenomena?
I don't even know what you're asking or what that has to do with the fact that we've all seen the pictures of the laser
It's not a
curving
phenomena,
upward.
dude.
It's not a phenomena. It's our math is wrong. Let's come up with an explanation. In this case, it's a mathematical explanation called terrestrial refraction.
Have you seen that?
Thank you, Meme. Hold on, Jesse. We got to caveat that. So, indeed, things being not where they appear to be at all times, like differentiation between days, definitely happens. So, like when I go to a small lake, I see things disappear, right? And rest assured, they disappear some days from the bottom up, some days from the top down, some days from the top and bottom simultaneously. Now, to be clear, this lake is small enough to where any alleged Earth curvature would be irrelevant. But that's not the point. The point is that, yes, we all see variations in what we see. The difference in this context of this argument is that it's claimed that the reasons we see things is called terrestrial refraction, which has an assumption of a radius, which makes it a phenomenon only in the sense if the Earth is a globe. So in one instance, we all see displacements optically, whatever they be. In the other instance, it's assumed that it's a phenomena in relationship to where it should be seen on a globe. But the globe has to be proven in the first instance for that to be a phenomenon. So that being said, what the heck is terrestrial refraction?
Maybe it's whatever causes that laser beam to look like it's curving up.
Well, if that's the case, that's a huge problem, isn't it? Shouldn't we see boats like way up in the sky?
Well, sometimes they do, actually.
No, we see them hovering in the horizon. is where we see them. It's called Fata Morgana.
But we're asking, what is terrestrial refraction? Do we not agree that there are conditions that can cause the path of light to be not straight in the air?
Yes, but it's unpredictable.
Right, but that's not terrestrial refraction, dude.
Right. That's just scattering. Like, there's miraging. There's, like, they've posted Fata Morgana there. And even there, see? The boat has entered into the angle, but the closing angle is too sharp to resolve the water.
So what do you think causes that laser beam to curve up or down or whatever it's doing?
I don't know. Smarter people than me know that answer, but I know this. If you got light shooting in every single direction, which is what happens, your net result is essentially just straight line. You can have warping in every direction. But the one thing that will never happen is something that is physically obstructed will never, ever appear out from behind what is physically obstructing it. And in the Andrew Thomas Yang paper, it says that.
So are you saying that if there was a county park boundary sign that was physically directly between me and the water line on the ship, that I would not be able to see the water line on the ship no matter what?
No, I didn't say that. Things certainly can sink and things certainly can loom. But the visual direction to the object will never reappear once it is already physically obstructed, and that is straight out of the paper. In other words, it's a one-way mirror. So if I see a lighthouse that is unobstructed and it is 31 miles away, or I see a ship that is 16 miles away that is unobstructed, it is because it is unobstructed. It's not appearing from behind a rolling ball of water. It is unobstructed. It is a straight line of sight to it. Because even in the paper on refraction, what is already physically obstructed will not reappear. In other words, like, let's say the bottom of something is cut off because of physical obstruction, and then it begins to loom. So it does that Fata Morgana thing. Well, what's going to happen is it's still going to appear to be cut off by that physical obstruction. More of it is not going to appear. And what's more is that paper specifically is talking about things that are perpendicular to the surface of the water, which means the horizon doesn't loom and the horizon doesn't sink.
Yeah.
So if
I want to add a caveat to that, if I can. So when you take a camera and you level the camera and you point it out at the horizon, what you'll generally see is roughly 50-50 distribution, as long as you maintain the level on the camera. So the top half of the image will generally be sky. The bottom half of the image will generally be ocean. And now you're going to have a very fine up and down in the center there. Now, when you angle the camera downwards, the majority of the bottom portion, right, will now creep up on your image. So you'll have like 75% water and 25% sky. That is because you've changed the angles that the light is entering the optic, right? So then they're being redirected onto a portion of the sensor, which causes it to render the majority of the image as water. Now, if it's true that refraction is causing a myriad of angles of entry possible to the camera, then why is it that with a level camera, you never see a 75% filled water in the image?
Because the refraction isn't strong enough, maybe?
Well, light, does it not go out in all directions from the target object, and is it not taking multitude of paths based on this assumption that light is curving every time it hits a different gradient?
Well, the only paths that get photographed are those which enter the lens. All the rest don't get photographed, right? But the bigger point is, if let's say we have a camera that's got 45 degrees of vertical field of view. We point it down 22.5, and that makes the picture 75% full of water, right?
No, the point I'm making, friend, is everything seems to appear to be up or down, looming, sinking, etc., in relation to the horizon. The horizon appears to us to be extended out into the distance further based on demarcation points, such as in the Black Swan being the oil rigs. So it's either what appears to us to be a greater or further distance. But generally, when we photograph from the same altitude, the horizon is pretty much in the middle, and everything else is up or down. Why isn't the horizon going up or down?
Well, it does. If the camera is actually level, the horizon does go up or down a little bit, depending on the conditions. Right?
Right. But in what range of tolerance?
Oh, I think I've seen it go up a couple arc minutes above eye level on some days, and then, of course, other days it's slightly below eye level.
Right. So, in the end of the day, what does that tell you?
Well, obviously it can't be both, and I'm pretty sure the water isn't 40 feet above me when I'm standing there looking at it, because it would rush in on me, right?
Right. So what does all of that tell you?
Well,
nothing is ever consistently where it should be, theoretically.
Well, yeah, my experience is that when my line of sight is right close to the water, all bets are off. The horizon and things floating on the water a bit out can either appear above eye level or below eye level.
Right. So what you're looking at is all optical effects, right? That's all it can be in principle.
Well,
and you can't know the angles. You can't know the angles to the objects because you can't even be sure where the horizon is at any given moment.
Right. I know the variation has to be optical effects because I'm pretty sure the whole ocean isn't tipping up and tipping down. But that doesn't tell me what the actual physical angle would be if I didn't have the variations of the optical effect.
No, the point is that you can never know the exact physical angle to an object at distance based on optical equipment.
Right. Nothing in this life is exact.
You can't validate the path of light. The angle of reception can't be validated all the way back to the target object. But yet the globe proponents require the assumption of that validation, right? And they say that it fits perfectly with the globe, yet there's myriad of observations that are beyond the limits that the globe claims are possible. So at the end of the day, both sides are left with things in the distance are optical effects. So why is it that the globe gets to claim geometric considerations over it and say, oh, if this is higher than this line or lower than that line, then the Earth can't possibly be flat, while simultaneously believing that light takes a myriad of paths through the atmosphere? It's like, okay, if the Earth is flat, then that means that light must be straight line rays that act in an ideal fashion. But if the Earth is a globe, light goes every which way to prove the Earth is a globe, no matter what observation you show me. That is unfalsifiable bullshit, brother.
Well,
so with that being said, I summarily dismiss all of your observations. Case closed. Next. You could continue with anybody else if you want, but I rested my case quite thoroughly and unequivocally.
Oh, okay. Thank you.
On your 105-mile observation, did you compensate for the tilt?
For which tilt?
Tilted the mountain away from you.
No, I just
So 1.5 degrees. Did you know that?
What's that?
It's supposed to be 1.5 degrees at that distance.
What is
the mountain is supposed to be tilted away from you 1.5 degrees.
Oh, Mount Shasta, the target mountain.
Yeah. Can you see 1.5 degrees?
No, not at that distance.
It's a degree, dude. Doesn't matter what the distance is, it's a degree.
So I'm not sure I'm following. So we've got this kind of conical mountain, and
it should
it's
be tilted away from you 1.5 degrees.
right. How would I determine if it was or not?
Well, it's going to change your angular size measurements, and it's going to change the height of the mountain. See, what is the point of all this, everything that I brought up? Remember what I said, you're cherry-picking data, your data's too clean? I've mentioned about, 5, 6 uncertainties or variables, things you didn't know about that you didn't take into account, but somehow your data matches. How is that even possible? Think about it for a second.
That's what I want to know.
Yeah, I gave you the answer. It's called cherry picking.
Well, I certainly didn't cherry pick the 30 shots to the mountain that's 75 miles away, all from the same location to the same target.
Yeah, that. You took how many?
30 of them.
Over how long of a time period?
A couple. I think there's dates from like 3 different years, but they're not all consecutive or something. But different times of year and different times of day.
But where in those is Earth curve?
Well, that's just a single point measurement to gauge the consistency of my method, right? Because we all want to know if our method is consistent.
So this is. So let me get this right. You did a bunch of measurements from one location, and you've extrapolated that out to all the measurements you've ever done.
Yes.
Yeah, exactly.
Okay. It's not really how that works, but.
Well, how would I go about this? Let's say I were
regular surveyor do it. What do they actually do in surveying? So what is geodetic surveying about your level? It says it's only level at that point. The plumb is only at that point. At the point of the theodolite, not at some region of space out there somewhere. This is what geodetic surveying says, not what I say.
Right? But
so what do they do? They take a measurement and then they do a horizontal reduction.
Yep.
But neither you nor I want to trust geodetic surveyors, right? Because they say the Earth is a globe, right?
You're testing. No, dude. Are the elevations that you're getting, are they based upon a globe? When you Google the elevation of where you are and what you're looking at, is that a globe?
No.
They're just listed above mean sea level.
Right.
Yeah, but how did they find mean sea level, and how did they find the elevation of your location? The elevation above sea level.
Well, in my case, I'm not that far from sea level, so they could have just measured the average sea level for a while and come up with a mean sea level.
Yeah, and then measured the height of the mountain. Now,
and then the mountain also is not too far from salt water.
So they're going to measure the angle, right? They're going to take level. They're going to measure the angle. Now, the elevation they come up with, if they presuppose a flat Earth versus presuppose a globe, are they going to come up with different values?
I'm not sure I understand. Are you saying that the mountain height and the observer height are not relative to what sea level would be at that location?
No, what I'm saying is that the elevation of, say, Mount Shasta, whatever mountain you're looking at from sea level, the angle you measure, right? So say I level the instrument and I measure a 1 degree angle. Now, if I know it's 100 miles away. Now, if I think it's a globe of 3,959 mile radius, that amount that I see is going to mean one thing, but if I don't assume that, it's going to mean another thing, right? Because you think that the mountain is, if it's a globe, then the mountain is sinking. And then if I can see 1 degree of it, that means some of it is underneath the hump, right? So this is how geodetic surveying actually works. So these elevations and heights, they're based upon...
Hold on just a second.
They're based upon an ellipsoid. They're not just measurements. They're measurements that have been mathematically treated. Yeah, I want to agree with. I want to deal with that too. What Joyce just posted too. Hold on a second. My oven's beeping again. I'm cooking a bunch of shit. So hold on.
Yeah, what Indio's trying to say there is, okay, from Helmert, Mathematical Theories and Principles of Higher Geodesy, though the Earth can't be reached surface-wise everywhere, it has been made possible to get a general shape of the Earth based on a law of formation, in whose principles are the assumption of a rotating body and an inward gravitational force. Oh, so is it the case that they're just measuring the Earth and applying a metrics of hard measurements against each other? No, they're applying them through a law of formation in which the globe Earth, having a radius, being a rotating body around an axis, and having an inward gravitational force are assumed and applied in the first instance before they give the final result. So it's not the case that they're just quote-unquote measuring the Earth.
I mean, that would be silly.
Since you were gone, Jesse, that was quotes from Helmert, Mathematical Principles and Theories of Higher Geodesy. 2-volume set, over 1,200 pages. Legit, the real deal, Shaquille. So when you ask, how do they do geodesy? They just go measure the Earth is not the answer. The answer of how they do quote-unquote geodesy in total is they assume the Earth's a globe in the first instance. And they shove their measurements up an ass of a matrix of transformation to fit their data to a globe.
Yeah, and then you're taking a derivative of that and saying my derivative, their values that they generated match a globe. Yeah, well, no shit.
So let's just say I want to do my own research. I don't trust geodesists, and I don't, whatever.
Trust got to do with anything. Why do you keep bringing up trust? What the fuck does trust got to do with anything?
Well, in other words, let's say I don't want to
trust
cite
your family, trust your friends. Like, what the hell does trust have to do with anything else?
Well, I mean, what I'm saying is, let's say I don't want to just depend on the words of the mainstream surveyors and the geodesists and whatever. Let's say I want to do my own research.
They tell you they're doing it. It's not their word. It's not our word. They say they're doing it. They're saying that they're reducing shit to a fucking Clark ellipsoid. Or in the case of the WGS-84 ellipsoid, that they're taking measurements, that they're doing a horizontal reduction to the so-called surface of this ellipsoid, assuming that a plumb line must goddamn curve in order to do it, right? We're not saying it, they're saying it. Of course they're going to get the result they want because the finished product is an ellipsoid, right? So I can take all the math in the world, and if I just projected the points on an ellipsoid, it's going to be an ellipsoid. No matter what. Right? So they have a premise. They have an assumption. A mathematical surface that they're projecting the points onto. They say it, not us. So the WGS-84 reference ellipsoid. Now, reference ellipsoid. It's a reference. And then the geode is the imaginary sea level. As if the sea was going under the mountain you're on. So when you do a site reduction, you're reducing it to, like, the ellipsoid. And then you get the tilt and all that shit from the fucking geode. But the point is that you could just go, like, to the edge of the sea, right? And you could measure the top of the mountain. Right?
Right.
And then you could take an altimeter and go to the top of the mountain and do the altimeter reading. Right?
Yeah.
And don't do any calibration. Don't fucking say, oh, this altimeter says it's 3,000 miles. Just get the pressure. Then you find a second mountain. Then you do the same methodology, assuming a flat Earth, get its height. Then you take your altimeter and go up there and look at the pressure and see if the pressure difference is different based upon your different measured elevations. Right? And then you create a calibration using that scale, right? Then you take a third mountain. And you don't even measure that. You go up with the altimeter, say, well, according to my calculations, it says this should be a 3,000-foot mountain. Then you go back down and you measure the height of that mountain, see if it matches. It's pretty simple. And obviously, obviously it's time consuming. It's not simple in actually like doing it. Obviously, it's time consuming, takes effort. I'm not in work. I'm not going to just like dismiss that. It's like it's like brushing your teeth. It's not that simple. But I mean, this stuff can be done, and you're not assuming anything. And you know what you're going to get? You're going to get the Earth's flat because you had a starting assumption. And it's going to be verified with an altimeter.
But
do you understand what I'm saying?
Wouldn't the same results be had on a globe, though?
You could literally fucking choose any arbitrary surface. Pineapple, pretzel, pizza, frickin' you name it. You have a starting assumption. So when they have an altimeter, right? Okay. So you're at a mountain. So when they invented the altimeter, how did they calibrate that, you think? They probably took it to sea level, right?
Probably, yeah.
Got the pressure. Then they took it on top of something what they thought was a known elevation. And that elevation was measured using so-called geodesy, right? So they have the globe height. And they said, oh, this mountain's 5,000 feet high. When it reads this pressure, I must be at 5,000 feet. Right? And they go all over the world doing the exact same thing. It's called affirming the consequent. It's just circular logic. But if they assumed a flat Earth, they could use the same procedure. Take the pressure at sea level, say this is zero elevation, take it on top of a mountain, and say this mountain's 8,000 feet. But instead of saying it's 8,000 feet up 100 miles away from the ocean, that sea level, I'll say it's not curving in that it's flat from the ocean to here. And now instead of being 8,000 feet, it's 4,000 feet. Because typically, we don't have actual vertical measurements of mountains. There's no mountain that's like a sheer cliff that somebody took a tape measure and threw it off the edge of the cliff and measured the height of the mountain. And then no mountain goes right to the sea anyway. So it wouldn't even be at sea level. So you're going to have a rise in elevation regardless. The point is a lot of this is just, it's affirming the consequent. And what AI was saying is that all these things, these optical observations, and that's what they are, they're optical observations. All you're really measuring is an angle that the light is hitting the camera or the device. That's it. And it's only valid at that point. And there are tons of variables. Like I said, especially for the globe. The globe just adds more variables. It's like if you wanted to apply Occam's razor is it's not a globe because you have to make a very convoluted freaking mental construct to even support that for 5 seconds.
Yeah, dude, you need a 2-volume set, 1,200 pages long.
Yeah, exactly. You're talking about Helmert's mathematical fucking and higher theories of geodesy is something like 1,200 pages, 2 volumes, and it's all freaking formulas. And it starts off with saying, "Oh well, we can't measure everywhere." so we assume a theory of formation and a rotation of the Earth. So we've come up with this geode thing that we're going to just project our measurements onto. So I want to show you another thing, Jesse. I don't know if I brought this up to you before. Do you see this? Fuck, it's wicked small. Hold on a second.
Oh yeah.
You've seen that before, right? Do you think that this is an accurate representation of how it works? Refraction works? In reality? Have I shown you this before?
No, Drace did last night.
Okay. So you see how the light ray is coming down from the mountain to the person's eye?
Uh-huh.
So, but it's the actual, like, okay, so you have the real mountain and then the illusionary mountain that's above it. Right? So the ray that's hitting this person's eye seems to be coming out horizontal from the mountain. You realize that his viewpoint would, when he looks, even though the mountain appears elevated, the image of the mountain is going to be the light that came in the direction of where he was horizontal. It's not going to look like he's underneath the mountain.
I'm not sure I'm following. It looks like he's seeing the mountain higher than it is.
Listen, this graphic is backwards. It should not appear like the mountain is elevated because the light comes to you. It should appear as the mountain should look as if you are looking at it from an elevated position.
Oh, the curve would be the other way?
No, I'm not talking about curve. I'm talking about this is refraction. This is not the curve's the other way. It would appear as if you're looking at it from an elevated position. Because the light that reaches your eye... I'm going to use a better graphic.
Thanks.
That shit sucks. That thing is just... Nothing against Drace, it's just too small. Here, I'm going to show you. Fuck, it's even smaller. Just give me a second. I just have to fiddle with this.
Yeah, sure.
Okay. Here, can you see that?
Let me look. Yes.
So, you see how it shows a ray that's curving, right? It goes from the top of sail, top of the mast. It's curving down to this person in this little motorboat.
Uh-huh.
Well, that ray, the normal path of that ray, would be up here into the sky. You would have to be, it would look like you were elevated at that position.
Do you mean to an observer at the top of the mast?
The illusion would appear as if you are a higher position than where you are. Because the light ray that's hitting your eye is a ray that comes from an angle that's going towards a higher position. Now, say there was no refraction, right? So the red arrow, the red line and the red arrow, that would be the non-refracted path. So that's the ray that you would see if there was no refraction. And then this is the other one, the curved one that goes down to the guy in the motorboat. That's the refracted ray. But the optical illusion is as if you're looking at it from the higher viewpoint. Their graphic is just wrong. Because for it to be coming from this, to look like this, would have to be coming from the bottom. So that would be a concave ray that would make it look like that. you understand what I'm saying?
I think so.
See how it shows you elevator map? So it shows the dotted outline of the boat, right? But he's looking at it from underneath. The optical illusion is if the boat is picked up and he is underneath it, right?
And is that not what often happens at the shore?
That you're underneath it?
No, that it appears above you.
Its spatial position is irrelevant. Doesn't matter if it's up or down. That's not the point. The point is the rays of light that are reaching your eye. What angle did they leave the object from? Whatever angle they left the object from that's when it's going to appear your viewpoint is from. So say we had some crazy refraction where the rays of light bent to your eye came only from directly above the boat, and they did a U-turn and came back down, and you looked up in your sky and you saw the mirage of a boat. It would look like as if you're looking at it from the top. But
you'd be looking up at it from the top, right?
But you'd be looking straight up over your head, but you would see an image of the top you would see an image of looking at the boat from above it.
Right.
Okay. That's why this graphic is wrong. Because the ray, for it to take this path of light, the initial trajectory, the ray that follows this trajectory originally would have been, 30 feet above this boat. So if there was no refraction and I was 30 feet above the boat, whatever image that is, that's the image I'm going to see it with refraction at the boat.
So we're agreeing that the path of light is curved. We just don't agree on the direction that it curves.
No, what I'm saying is that nobody actually observes this. Nobody actually observes so-called refraction, where things are so-called being picked up, but it's as if you're looking down on the object. Right? When you did your observation, right, of your sign, right, and the sea appeared picked up, it did not appear like you got picked up, and now that you're looking at the sign to the waves lashing against the boat from a higher position, did it?
Well, there wasn't a lot of waves at all, really. But I mean,
what I'm saying is, it didn't seem, the image doesn't seem like you picked the camera up. Like if I took the refracted image and I waited for some crazy day without refraction, and then I'm like, okay, I'm going to take a picture at the elevation that matches this. If I put the camera up 30 feet, it isn't going to be that. It isn't going to look like that.
I don't know. It might.
Listen, there is no I don't know. Because light, a source of light, reflected or a primary source, right? Where the source that generates the light itself. Light is sent off in all directions, right? Every direction, spherically in every direction.
Right.
So a particular ray, let's call it a ray for the purpose of this, even though they're not actually rays. Let's just call them rays. A particular ray will reach the eye. And that ray had an initial direction when it left the object.
Right.
And if it curves, right, curves down, right, so say it's ejected from the object at a 45-degree angle up, but it curves down into some dude sitting in a motorboat. Well, if it continued on that 45-degree path, it would reach some point that's looking down at the object at a 45-degree angle. That's the ray you're going to see. The ray that left the object at a 45-degree angle above it. That's what it's going to look like. These graphics are I wouldn't call them deceptive. Maybe they just don't know. I'll give them the benefit of the doubt. Because if you look at, have you ever seen? I'll find another one with a fish. They always show the fish one. Hold on a second. Fraction fish. Where the fish appears displaced in the water, right?
Right.
Here's one. That's actually not a good one. It sucks. See, look at this. See how the light rays coming from the top of the fish? It's going up to the water. And it's bending.
Uh-huh.
And because of the way we see and the way our distance cues are, so we see the fish, the light is hitting our eye from a certain direction, but the light that's hitting us from a certain direction originated at the fish at the top, not from the front.
Right.
So if you actually ever seen this in real life, you don't see the fish's eyeballs. You still see this top of the fish, but he's moved over a foot.
Right, I've seen it.
Okay, yes, exactly. So you've seen it. You're not seeing the fish. You're not seeing the fish as if he's just like, just moved to the side. You still see the top of the fish. But the top of the fish is moved over, right? As opposed to the fish. As opposed to if you were in the water, right, or there was no refraction, and you were just looking at a fish from an angle. You understand what I'm saying?
Absolutely.
Okay. So these graphics that show something just picked up, as if you're looking from underneath it, no one's ever observed anything like this ever.
Well, naturally, the amount of bending that you get over water is not measured in so many degrees as a fish would be, but rather, say, arc minutes, a fraction of a degree, right?
Yeah. I understand all that. But the thing is, what is it going to look like? Like, I know it's a little bit subjective. Should it look like this? Should it look like that? But we know that if the light is doing this arc, that means the origination of that light, your viewpoint will appear as if you're looking at it from an elevated position. It isn't going to appear as if it is picked up. Right? I can see more of this boat than I should. Right? I should see, well, if it's a globe, then I should see, 10 feet of it, but instead I see 100 feet. It's because that boat is getting picked up over the horizon. That is not it. That is definitely not it. It should be, the light that was going to a point that would normally be 100 feet over my head, that's the light that's reaching my eye. So whatever view you do, if anything's being refracted up, it should actually look like as if you're looking at it from a higher vantage point.
But if the refraction only gives you a vantage point of, say, 100 feet at several miles, that's still an extremely shallow angle.
Well, let me ask you this. Can you tell the difference between, I've done this test myself, 15 feet above sea level versus 100 feet above sea level?
You mean how much of the top of a ship you can see?
Just looking at the ocean. Just looking at the ocean, ships out in the sea. Can you tell the difference between looking at it from 15 feet above sea level, what everything looks like out in the ocean in front of you, versus 100 feet above sea level and looking at the ocean? It's very easy to see the difference in the angles of everything out there. It's easy to detect. It's easy to detect like a difference in elevation of like 20 feet. But there's so much refraction being claimed and things being lifted up. If you stick it in the calculator, you're hundreds of feet higher than what you're supposed to be. That's how it should look. As if you were elevated hundreds of feet and you're looking over the horizon even more. Not that the objects in the distance are picked up.
So if I were, let's say...
Yeah, you just posted this, right? You just posted this thing.
Yeah.
Okay.
But that's 40 feet.
Why can't I see the top of the building? Why can't I see the top of the building surface? When you pick up an elevation, I should be able to see things that are like my eye line's parallel with the top of the building. If I look at it from a higher viewpoint, then it's not parallel. I should see some of the surface. See, this is exactly what I'm talking about. Things are not appearing in the bottom image. There's there's mad mirroring here. Why did you use this?
It's what I had. That's what was there. I took a picture of it.
Dude, there's mad mirroring. You see that?
Oh, absolutely. They both do, actually.
Yeah, I can see. Yeah, I can see the other one. Anyway, the point of what I'm saying is the refraction claim, the refraction claim of, we see things picked up from or under the horizon. That's not even how it should look. It's not even an accurate description of what the physics should be.
Well,
so have you ever seen have you ever heard the term Flying Dutchman?
I have heard the term. I think it's about a mythical ship that sailors like to come back and tell about during their drunken parties.
Yeah. I mean, that's where it kind of evolved to. But there was the other one where, it's a common observation in the Arctic to see ships or icebergs floating above the water, just hovering. Right, hovering in the air.
Uh-huh.
Have you heard it? This is what looming actually is. Ship floating above the water. Above the horizon. Not on the horizon, above the horizon. Ship floating up in the air. None of these observations are as if the person is looking down on the iceberg from this lifted up thing. But the only way for light to bend in the way you think, this curved down light bending, the only way this can happen is if the light ray starts at an angle from the source. And it isn't just me that says it. So Drace actually posted something a ways up. I don't know if he brought it up before. So this model, this model they made after the fact of what do you call it? A laser test they did. So in order he used standard refraction. He used David Bricker right here. So he used the standard using the 1972 standard atmosphere. He modeled refraction across 150 kilometer light path.
Guys.
Right? Hello? So cool things, right?
What exactly did he do?
Moses.
Well, they did a laser experiment, a 3-frequency laser experiment in Hawaii, and as part of his master's thesis, because he was part of the research team, right? This is after the experiment. He modeled how the light should behave using the 1972 standard atmosphere. So he modeled it with ray tracing, the so-called predicted curvature of the ray. And it turns out that it didn't match reality. But he didn't make the prediction first. So I just took a graphic I want to show you.
You know, I think you gave me something about that a while back, and I read it, and it didn't seem to me that he was saying what I thought you were saying he said, but now I've forgotten what the details were. Could I reread that and then we could discuss it?
Well, no, I just want to show you this particular graphic. Okay. It's not even, or I can just read you the part. Hold on. In order for the ray to reach its predefined endpoint, the laser beam must be aimed slightly above the target to correct for atmospheric refraction. Right?
Do you believe that?
That's your model, dude.
I'm not championing a model. I'm trying to just understand.
That's the refraction model where light. You didn't observe curving down rays, dude. You inferred that from your observation. You didn't observe it.
Well, I measured the angle of incidence.
Okay.
And they were arriving.
Yeah, that's fine, but it's an inference. It's an inference. It's not an observation. You didn't measure a curved ray.
Correct.
Yeah. Okay. So you didn't measure a curved ray. You inferred that based upon what other globers have told you about what rays of light bending down towards gradients.
Well, I measured it angle of arrival, its angle of incidence, and it was coming from a direction where I know the target is not. So logically, it couldn't have followed a straight path and arrived from a direction where the target is not, right?
Yeah, but you have no idea where it deviated from the straight path.
Oh, okay.
And you have also no idea, like, what it could have, like I said, it could be concave ray.
What's that?
It could have been a concave ray. It could have been. We're getting off the point.
Wouldn't that have caused the ship?
So in the point, I just don't want to get away from what I was talking about before we go way down that rabbit hole. Okay, so I'm going to just take a screenshot of this. Hold on, I want to show you. This is not my this is the claim, dude. This is the claim of atmospheric refraction bending light rays down. This shit has to be true. It's not optional. What I'm saying about like what it should look like, it's not optional. It has to be true. So this is a graph of the ray of the path. It has to reach 60 meters above where the laser starts and above where the end point is. Because it has to arc. Because it's always bending down. So if it's always bending down, you have to aim up. Otherwise, it'll just bend right down into the ground, right?
Right.
It'll never reach the target, right? Think about it like this, right? I'm shooting a bullet. I can't aim right. If it's 1,000 meters, I can't aim right at the target. The bullet has drop, right? So I have to aim up a little bit so that the bullet takes a parabolic arc and drops into the target. Well, this light ray is doing the same thing. If it has this constant gradient drop, then you have to aim up for it to drop into the target. Right? So that means the only light rays that are ever going to hit a target, your theodolite, the camera, my eyes, are going to be the rays that are aimed up. And the rays that are aimed up is going to make the view look like as if I'm looking at it from an elevated position, as if I am above it. This is a necessity. It isn't like an optional thing. And this is an Achilles heel for all this lifted up over the horizon shit. Because nothing ever looks like you're looking at it from above it. Especially like the black swan. So take the black swan, for instance. Does it look like you're looking at those oil rigs from up above them? Or as if you're still below them? But they're supposed to all be being lifted up. Fucking, the ocean too. So the ocean, because we're talking about the horizon, so the ocean has to be lifted up as if you're looking from above it. Actually, it's not being lifted up. You're being lifted up. Your viewpoint. Because the rays that would reach that viewpoint are the ones that you're seeing. The rays that would reach the 100-meter viewpoint are being bent down to the 15-meter viewpoint, and that's what I see, as if I'm viewing from 100 meters high. Do you understand what I'm saying?
Yeah.
Okay, then. Then there is no argument. There's really nothing nobody can say about it. That's just the way it is. This is the model. You can't, it's just the way it is. And it's not me, being a dick. This is what the model says has to happen in order for this to be a legitimate hypothesis for why you can see things that are too far. It has to happen this way. It can't happen another way. I mean, it can, but then it isn't going to be like it bends down, curving all the time. It would have to be something else.
So let's put some numbers on this. The building I showed you in that picture that showed it from two different heights was 21.2 miles away. According to the standard refraction claim, the change in angle would be 0.023 degrees. So that would be the equivalent of being raised up enough to be looking at the building from a less than 0.03 degrees. Do you really think a building 20 miles away would look any different from a 0.03 degree angle difference? Could you really see much of the top being only 0.023 degrees up?
Probably not, but that's a little deceptive.
How so?
Okay. So how much of the building is missing?
It depends on the observer height.
Oh, really?
Well, in my location, yeah, because it's kind of a cold area here, so we don't get as many hot days. So
this is taken 40 feet above sea level, and this is taken 100 feet above sea level.
Right, you can see more of the building is visible on the out from the higher observer location.
Okay, and why do you think that is? Because you're seeing over the curve of the Earth.
Well, I mean, it sort of matches the globe prediction, but I'm not saying what causes it.
How does it match the globe prediction?
Well, if you go to the Earth curve calculator and put in those two heights and estimate how much of the building should be missing, it's 187-foot tall building standing on about a 50-ish foot high hill. So you can kind of figure out how much of the building should be obscured if the Earth was a globe, and it's reasonably close for whatever reason.
Hold on. Let me ask you this question. The bottom image, that mirage line. If that was gone, what do you think we'd see? Water?
I don't know.
You don't know. Do you think it might look like the top image?
I don't think so, because the further down I go, the more gets obscured, and they all have that certain mirage line, but it's kind of similar in each case.
Okay. Lower down you go. Changes your angle to the building, right?
Right. And at 21 miles, that change is a very slight change.
So if there's a marine layer that's 2 meters, say, at however distance this arises, say there's a marine layer where this miraging is, this mirroring is happening. Marine layer of air, some turbulent air, whatever the hell, right? It's cutting it up. It's 2 meters. Isn't going down now? It's the same as like having a brick wall there. You understand what I'm saying?
Yeah, and that's why
there's a brick wall there. If I'm at one elevation, I can see over the brick wall, and I can see more of these buildings. But if I lower myself down, lower than the top of the brick wall, and then I keep lowering myself, I'm not going to see any of those buildings.
Right. No, I get that.
So this marine layer is just blocking everything.
Yeah, I'm not making any argument from the obscured bottom. You just asked what I'm that saying, building looked like from different heights.
You're comparing two things, right? You're comparing from one elevation, shit's all mirrored. Obviously, there's some condition of the air that's not letting the so-called true light get through, right? And what you're getting is light that is reflected or refracted or something. It's hard to know where it's being reflected. See, because this mirroring, it could be a reflection or it could be refraction. It's hard to say. I tend to think it's a reflection.
Yeah, my only point with that two pictures was it illustrates how the top of the building appears from two different elevations that are 0.03 degrees apart. Those two heights are roughly 0.03 degrees apart. So if you take a picture of the top of that building and then you go up 0.03 degrees and you take another picture, that's what it looks like. And I don't think
the problem. Hold on. The problem with difference of comparison is because of the clarity of the images. Because I can see a difference. I can see the difference in elevation.
It's definitely more clear at the higher elevation.
Look, so you got the arrow at the bottom where it says View Towers, right? And it has the big, the white building. It's dead center of the image. Well, not almost dead center. Okay, look at that. Look at the line of the roof, right? And then look at the other one, the line of the roof. Does it appear elevate? It appears to be an elevated position to me. It appears like you're higher relative to that building.
Oh, you mean because of how
It just does to me. It appears like this does not look like, and regardless of being cut off or not seeing the bottom, just the angle that you're looking at all these buildings appears to be from a more elevated position.
Well, I mean, I don't know how you could tell because I didn't particularly level the camera. I just pointed it and shot. So if I had pointed the camera down, the building would look higher, right?
No, what I'm saying is the angle that you're looking at the buildings, just the angle. One appears as if you're looking like straight across, and the other one appears as if you're looking at it from an elevated position.
Well,
to me, it does.
I still can't see the top surface on either one of them, but anyway.
Yeah, but the bottom one looks like you're looking at it from underneath.
Why? How do you figure? They were both below eye level.
How are these buildings below eye level? Let me see that.
I mean, if you like take an auto level or a water tube level or whatever and set it up, that building appears below eye level. If you're, I did it at 58 feet. I haven't done it actually at 48 or 40 feet, but it was enough below eye level at 58 feet eye level that it probably, the top would probably be right at eye level for the 40-foot observer.
Well, I'm just doing something. Why do weirdos always send me freaking friend requests?
Hey, I sent you one once. Of course, you accepted it.
No, like, yeah, I didn't. Just random people, dude, send me friend requests for no reason. They're on the server for like 30 seconds and they're sending me a friend request. Hold on, I'm gonna post both images. So hold on.
The lower image is definitely more blurry on the top of the building because the line of sight is cutting closer through that marine layer.
This to me seems like maybe it's probably from the shape of the little thing that's on top.
The air handler or the penthouse, I'm not sure.
Yeah, whatever that is. It's probably the elevator and like the air conditioning and stuff. But it does seem like it's a slightly looking down on it. I mean, but the thing is, the way it, to me, you should calculate it is, okay, say you have an object and you could see 20 feet of it, but you're not supposed to see it, but you see 20 feet of it. And they say, oh, it's being refracted up over the horizon. Then you punch in the curve calculator what elevation you have to see that. You understand what I'm saying? What elevation should this be visible? Oh, I see this, this building, 20 miles away. Right? And I can see 50 feet of it, and 100 feet supposed to be hidden by the curve of the earth, but 50 feet of it's being lifted up or something. Punch in the curve calculator, the elevation you have to be to see that. You understand? It's not just the angle. And yeah, that might be a small deviation of angle, but just from doing my own observations, I know that there's a big difference between looking at stuff from 100 feet and 15 feet. 10 times higher. Nearly 10 times higher. I've done this observation, so I can go. So I live near Revere Beach. They have a parking garage that's 100 feet exactly above sea level, and then they have a what do they call it? Not a gazebo. I don't know what the name for it. It's like a covered covered terrace. And that's like 15 feet above sea level. So they have markers, tidal markers. So that's 15 feet. So I've done observations from that point in the top of the freaking parking garage. And believe me, they look way different. They don't look anything even remotely similar. And even though for something that's 30 miles away, say, the angle is significantly different, I've just never, it just doesn't look like that. And like, you can call that subjective or whatever. Especially for some of these long distance observations, like Peak Gaspard. That does not look like you're looking down at it from, some crazy higher elevation.
What equivalent of elevation would you be looking at it from?
I don't know. I haven't really gone back because I just thought about this a couple weeks ago. I've been busy. I haven't had time to go back and check numbers and shit, which I probably will at some point.
Okay, ping me up when you do, because I'm interested in what, the difference between what it should look like and what it does look like.
Yeah, well, I mean, what it should look like is as if it's not picked up, but as if you're picked up.
Right, but by how much?
Hold on a second.
What?
Oh, it sounds delicious. Oh yeah, delicious.
I'm gonna grab some water. I'll be right back.
You grab that water. You get that water. Come back for the slaughter. Go get that water.
I'm back.
Bro, is there an infinite amount of propagation angles relative to the reception angles with the constraints of the angular resolution of an optic with an angular field of view? The answer is no. So that being said, why would one expect to be able to see with an optic that has limitations in 3 categories? The entirety of an object at all times, at all distances, at all angles. The answer is you wouldn't. So the globe Earth promotes the idea, or globe Earth proponents promote the idea that I can't see the bottom of something, therefore it must be obstructed by a physical hump of Earth curvature. And whenever you show me a counterexample that shows the object in question that should have been obstructed but is now not obstructed, well, then I'll just beg the question that I already know the Earth is a globe, and then I'll say that light's curving, and that's the answer. Why is it that the globe must always recede into a misplacement of physical locations by confusing them with optical location? It seems the modus operandi for a matrix of excuses that make the globe unfalsifiable. For example, Indio said, take this data to a Earth curve calculator. Well, what's the Earth curve calculator do for you? It'll tell you the ideal based on ideal globe geometry of where you have to be to get a straight line shot to an object, and how much of it would be hidden based upon an obstruction as an off angle off an apex of an arc in between point A and point B, right? They'll tell you that, but then you have to apply, well, what about things that don't fit that, which is many, 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 in fact, all observations. There's no observation that fits the globe Earth geometry perfectly. Zero. Not one. Not one. Not one. Not one. I'm going to repeat myself again, ad infinitum. Not one observation fits it perfectly. So for all of the ones that are dramatically different, you must go to your Earth curve calculator, put it in there. Now, but what does the Earth curve calculator do with your observation? Because you'd say, I could see this much of the thing. Here's the supposed curve of the Earth. How do I solve this problem? Well, the globe Earth calculators apply terrestrial refraction to solve the problem. Now, of course, anybody worth their intelligence will understand that that's an ex post hoc argument or an ex post hoc rationale, because there isn't actually any measurement of the ambient refractive conditions in the atmosphere at the time of the observation that's being applied. No, it's a mathematical construct that's being applied. So it's just how much refraction would be needed in order to justify this observation, and this calculator will tell me so. Therefore, that must be based on the fact that I already know the Earth's a globe, which is presuppositional reasoning, to give me my conclusion. So you go, you put in the numbers, and what does the Earth curve calculator do? Does it input paths of light? No. This is what it does. This is what it literally says it does. Sometimes the Earth appears flatter than it is, almost as if the Earth is a bigger globe. What the fuck? So what do they mean by that? Well, I'll explain it mathematically, and you could see this practically. I've done it live here on the air many times. Anybody else can go do it themselves. Just go to the Walter Bislin's calculator right now. Go in there, put in an observation, and look at what the math does in the little blocks. So you'll change the observation, and then it won't fit, and then you'll change the refraction slider, and you'll notice what happens. What happens is that the radius changes. The radius of the Earth in the model that's in the calculator changes. And the reason why this is done, it's inflated. The first standard is 7/6, so it inflates the radius by 1/6, right?
Yes.
What this does, okay, according to the circle segment formula, it lowers the sagitta, which is the midline to the apex arc of a chord line between point A and point B. So what it does is it physically, quote unquote, or mathematically, more like it, lowers the hump in between point A and point B to give you a straight line shot to the observation target. That's what it does. And they call it refraction, and people assume this is about light, but it's about just changing the geometry to match the observation in an ex post hoc fashion. Now, this refraction slider goes up to not 6 million radius miles, not 60 million radius miles, but it slides all the way up to a globe of the size of 60 billion mile radius, just in case you have an extraordinary observation that doesn't fit your globe model. You can shove refraction so far up its ass that it comes out your anus and then takes a swing by Neptune. Now, of course, I said that all with a lot of rhetorical flair, but it doesn't discount the validity of my point, which is that the globe just has a matrix of excuses for all of the optical phenomena that doesn't fit their claims, which are first orderly based on optical phenomena. By their own admission, which is an affirming the consequent fallacy, was if the Earth was a globe, I wouldn't see the bottom of things. I don't see the bottoms of things, therefore the Earth is a globe. Because they can't fathom an alternative explanation. So they think their explanation must be true. And therefore they assume it true, then presuppose it at the beginning of their line of reasoning when they make this Earth curve calculator. Yep. Well, that's that. So, where's any of the proof of any of this nonsense? What say you, Mr. Jesse?
Oh, well, I don't know.
Well, I wasn't expecting you to know, to be fair. You know, people can post affirming the consequent fallacies, the bottom of a boat missing. Why does this thing appear to be in a differential placement in my field of view from where I geometrically expect it, even though I have no way of knowing the path of the light in which it's informing the camera? They could do this ad infinitum. They can say, oh, all swans are white and any black swan is just painted with spray paint. It's highly irrelevant because the summary of their presentation of what they call evidence is all based on circular reasoning. It's only true if the proposition that it relies upon is true in the first instance. You can't prove the proposition true with circular reasoning and then borrow the conclusion from that circular reasoning to input into a different circular reasoning. But that's what a majority of the globe proofs are. They're just a long-form chain of circular reasoning that shifts the ball around under the cup so you don't notice that they're switching from argument to argument and just inputting a conclusion that hasn't been proven. So we all already know that optics do weird things, that we can't be certain about the physical locations of things based on optical phenomena alone.
And actually, I think if one were to measure the angle to the where the water line meets the platform in the oil platform pictures, it would actually be above eye level, which would mean that not only would the radius be very large, it would be concave.
Right, so you're a concave earther. Thanks for coming out. We knew you were a scumbag all along. I rest my case. You're hereby canceled. Your credit cards are revoked. Wait a minute, you're not a concave earther?
Nope. I'm just saying.
All right, cancel that order. Cancel that
Social
order.
credit reduced.
Yeah, exactly.
Just don't take my carbon footprint away. I like my bonfires.
Go to the gulag, sir.
No, I'm just saying if one takes the oil platform picture as an accurate representation of the shape of the Earth's surface, then it actually is evidence for concave, because where the water line meets the structure is actually above eye level.
Well,
that's
an assumption on your part to this point, correct?
Well, I've filmed and published on my YouTube my own black swan scenes from my area, and I've shown it. It wasn't oil platforms,
Okay,
but
so
it
you're
was.
saying, yeah. So you're saying you have evidence that the horizon is above the midline of your viewpoint.
No, it's above eye level. Like if you took and extended a flat level plane out from your eyes straight out, it's above that under certain conditions. Which,
Right,
if
but we already all conceded that what that just means is that the angles of the light entering the optic make the image appear that way. That's the problem. No matter what, that's the end result every time. Because that's how images are formed. They're not formed any other way. But the whole point of the black swan, right, is what? Is that the horizon is not a geometric location.
Ah.
Correct?
I don't know. You guys argue with the black swan. It's your argument.
Yeah. It's essentially proof that images are created with optical effects, not necessarily geometric placements. Because that's the claim of the globe for the longest time, that the horizon is the arc of an Earth curve hump that's blocking things. That it's the edge of a sphere that's in between point A and point B that effectuates itself as a hill, blocking something behind it. That's long been the claim of the globe proponents. That's been their claim into the past, where they say, oh, I can't see the bottom of a ship going out. That means the water's curved and the boat's going down compared to me, and the water curve is rising and getting in between us. And the edge of that is the horizon. That's been the globe claim for a long time. Utterly destroyed. Not that the black swan was the first destruction of that proposition, but it was an eloquent one. Quite precise and quite nasty. Which made a lot of globers flip their script and start saying that they always said the horizon was nothing but optical. Right? Even though we have it on recording, multiple times they showed up on various shows like Nathan Oakley or here or other places, saying that the horizon is the edge of a sphere. The horizon is Earth curve. And of course, they only say that because they assume that it must be so, because that's the only thing that can block something. Because they're assuming that it's blocking something. They're assuming that when they can't see the bottom of something, it must be blocked. Therefore, because it's blocked, it must be blocked by something. What's it being blocked by? Well, the only explanation I have is the curve of the Earth. I already assume it's a curved Earth, so therefore I'm going to affirm the consequent and do some bias reaffirmation and just assume that that's what's happening. And the black swan eviscerated that. For the same reason why presenting a black swan to a person that says all swans are white would eviscerate their position.
But you agree that there are situations where it is blocked, right?
What do you mean blocked?
In other words, there are situations where the bottom of something is obscured by water, right?
Oh, of course. Waves. Sure.
Well, but I mean, even cases where it's not waves, right?
Like what?
Oh, did you see that picture I posted earlier?
You got waves, you got tidal bore, you've got swells, you've got undulations.
He's equating a mirage to Earth curve right now.
Whoa. A mirage, though? A mirage isn't really obstructing anything. It's just overtaking the amount of resolvable light from the other object. The other light, rest assured, in a mirage, the other light is penetrating the mirage to some degree. It's just not enough to resolve.
So I take
unless you're saying that a mirage is being caused by like an ambient increase in humidity or some kind of fog or something like that, then, well, yeah, fog and all that stuff, clouds, low-hanging, thick fog can definitely block something. And technically, fog is made up of water particulates, so you could say water can obstruct the bottoms of things that's not a wave, sure.
Did you see those pictures I just tagged you with?
Let me look. Asking a blind guy if he can see the pictures. Good grief. Hold on, let me get out my Braille interpreter. Dude, what? I thought you said I was going to see water obstructing something.
Okay, see the bottom picture?
Yeah, what about it?
See the building called the View Towers?
I see some writing that says View Towers. Yeah, what about it?
Okay, and it's pointing at a white brick. Well, that building is in Victoria, Canada. You can go there and look. And it's standing on a hill that's 50 feet high above sea level. And that entire hill is obscured by the water, right?
No.
No, I mean the hill underneath the building. Do you see any land underneath the building above the water?
On the bottom image, no. I don't see the land being resolved in the final image.
No, I said obscured.
Yes, yeah. But you see, hold on, friend. This is the problem, okay? We're going to elucidate it right now for the audience. The water is not obscuring it from the evidence that I have from this image. All as I know is that I can't see the bottom of the building. In order for the water to be obscuring the building, I have to know that the water is physically in between point A and point B. I don't have that information from the image.
Well, but I mean, the point is, you know there's 50 foot high.
The point is that you can't see it. And you're going to make an inference that it's being obstructed by an object when you don't have enough evidence. That's right. My point. You're assuming physical locations based on optical information.
No, I'm just simply asking you on a flat earth, why can't I see that 50-foot high hill that's underneath the building? Why does it look like water is there where that 50-foot high hill should be, right?
Okay, so your question is why optics, which have an angular field of view, don't have an infinite amount of resolving angles relative to the propagation angles? That's your actual question, whether you realize it or not.
Are you saying that the 50-foot high hill is just too small to be resolvable, and so it appears as nothing, and the water just appears there?
Well, as you approach 0 degrees in your field of view, right, and you have less and less available resolving angles compared to the propagation angles, the resolving angles subsume the propagation angles, right?
But
I mean, you do agree you can't see at infinity. You can't see at 0 degrees, and you can't see without the limitations of angles, right?
Right, you can't resolve below your limit of angular resolution. But I don't believe anything in this picture I don't believe the 50-foot high hill is smaller than the limit of angular resolution of my zoom lens here. Because obviously things much smaller than 50 feet are showing up. Like you can see like some towers and stuff that are maybe 20 feet across or 10 feet across.
Whoa, dude. That's only one factor. There's two factors, at least. It's not just their angular size compared to your angular resolution limit. It's where the angles of propagations are compared to that limit. So if something was straight in front of you, right, then that would be, as it approaches the horizon, obviously it's going to approach closer to 0 degrees. Right? Not to mention all the ambient occlusion from the atmosphere being the densest there, right? So you have, that's three factors.
But
So, for example, I'll give you a quick math. So, at a 6 foot tall guy standing just on the ground, and he's looking out. Okay, if you draw the triangles out of his angular resolution, right, 0.02 degrees. Coincidentally, the bottom leg of the triangle reaches a plane extending out from his feet horizontally at approximately the same distance that they claim the horizon begins to cut things off at that same differential.
I'm not sure what the relevance is here because my observer was 40 feet high and I had a zoom lens which has hundreds of times more, probably thousands of times more angular resolution than a human eye, an unaided human eye.
Hell no, dude. Hell to the frick no.
Thousands.
Where in the world, dude?
160 degrees in a circle, dude.
Fuck, man. We're not talking about 27 megapixel cameras, dude. The megapixels is the sensor, not the angular resolution. Pixel density is not the same as angular resolution.
I know, but if you have say a telescope, that increases your limit of angular resolution, right?
To a degree.
Okay. My theodolite says it has an angular resolution of the telescope optics of 3 arc seconds.
That's horseshit.
Oh, okay.
I tell you it's horseshit. It's easy to demonstrate it's horseshit. Because the crosshairs. Crosshairs themselves, right? They're inside the lens.
Uh-huh.
They're going to subtend some angle, right? Out to infinity. They're blocking your view, right?
Right.
What's that angle?
I don't know.
What's that angle 100 miles away?
Yeah, I don't know.
That'd be pretty big.
But
that'd be pretty massive.
It would be massive. But you don't see that when you actually look to the optic. You don't perceive any of that shit.
The crosshairs actually have a little break in the middle so that you can actually look right. They don't actually occupy they come to an end right near the middle, so they don't actually form a complete cross. So you can look through the middle of the crosshairs. It's open there.
Dude, how come in your JPEGs here you don't have the observation distance?
What JPEGs were?
These two things where you falsely said that the water is obscuring the building when that's not the information presented in the photo. But anyway.
Oh, I'm sorry. I can get those. I put the GPS coordinates of the observer so anyone could get. It's not like I'm trying to hide anything for sure. I made this to show someone that the water appears in the place that a 40-foot high proposed laser test site would be. And I put the coordinates, but I didn't.
Well, do you remember off the top of your head?
It's roughly
go look up coordinates.
Yeah, no, it's roughly 22 miles.
22 miles, 50 feet, right?
I'm not sure what the 50 foot is. The foot of the building's about 50, yeah.
So your claim that was 50 feet of the building was obscured by water, meaning that the water, if you're talking about the water that's part of the ocean water or lake water or whatever it is, if it's obscured by it, then in order for that to be true, then it means it has to be in the line of sight between point A and point B.
Well, actually, I said the 50-foot hill underneath the building was not visible. But
fine. That's correct. But
so that's
same point applies.
So that's my question is, see where there's kind of a darker orange text that says proposed laser site near the right?
Mm-hmm.
Well, if you had a guy there with a laser, he's 40 feet above the water. And then you've got a guy on the other side, also 40 feet above the water, and yet you couldn't see him because you can't even see that location, right? So that's my question: is how is this water blocking a line of sight that is 40 feet above the water at both ends?
Not the water.
Why are you begging the question that it's blocking?
And obviously, it's the water. Okay, I asked you specifically the mirrored part. That mirrored part, which obviously is not water, what's that blocking? There's a vertical section, which is obviously a mirrored image of what's above it. So, where that line is, that dividing line, right? There's some space in the image, some vertical space, goes horizontally across the entire image. What's in that space? If that mirrored part was disappeared, what's in that space? It's not water. Right? It's not water. You think it's water? You think that where that mirrored image part, that's actually water?
I don't think so, but I mean, I don't know exactly. But I'm not sure what you're asking. The point is, the building.
I'll draw it, dude. I'll just draw it.
The building is on a 50-foot high hill. Are we in? Are you contesting that?
No. Hold on. Just bear with me here. I'll show you something. Let me show you something. Fire Marshal Bill.
Man, I wish I wasn't freezing to death. I could use my device and actually do some calculations.
But it's like what it seems like to me. The issue is that all you're able to see is that it's not visible, and then you're claiming that that's because of an obstruction, right? And then your evidence for that is that it's not visible. Do you see how that's circular?
No, it's just that I know something's there, and instead of seeing what I know is there, I see water, which should be 40 feet down.
That's exactly what I said, right? You took the observation, and you noticed, hey, I can't see something. And your conclusion is that it must be physically obstructed by something. And then your evidence for that is that you cannot see it. But that's circular reasoning.
Well, I'm open to someone suggesting what's actually happening.
It would be like saying...
So you're open to someone suggesting that you shouldn't use circular reasoning? Yeah, we're suggesting that.
That would be good, yeah. Well, it would be like me saying, well, I can see things falling down, therefore I'm going to claim that there must be invisible creatures that pull them down. And then my evidence for that would be things falling down. That's completely retarded. And yet it's the exact same logic applied to the example that you're providing. Because you're providing a photo of something that is not visible, then you're claiming that there's a physical obstruction, and then you're pointing at, well, look, it's not visible. So how is that logical or a valid argument?
You lost me.
We know.
Because you don't understand what circular logic is, probably.
I can explain it to him. So a sphere is made up of essentially an infinite amount of concentric rotated circles. So if you have enough circular reasonings, you end up with a sphere. Therefore, the Earth is a globe.
Makes sense to me. Hey, Jesse, did you see the image I just posted with the red line going across it?
Let me look.
I drew a red line where it looks like it's mirroring the mirrored image of the building. What's below that line? Is that water or air?
I would say that's probably air.
Okay, so where is the building cut off? Is the building cut off at the red line or at the water?
At the red line.
Okay.
Because what's below the red line is just a reflection of what's above.
It's not Earth curve blocking the bottom of the building, it's air.
Okay. So tell me about this air.
What do you mean tell you about the air? It's obviously air blocking it, not water. It's not a water horizon blocking the building. That means that this is an optical effect. This thing, it's not Earth curve. It's not a ball Earth edge. It's air. It's probably what's called total internal reflection.
Okay, so we've got the thing we're looking at and the observer both 40 feet above the water.
Yeah.
And yet that line of sight appears to have water. So is the light basically curving downward, skimming the water, and then or going downward on an upward arch like a big smile, skimming the water, and then
refraction
coming back?
Isn't the only choice. There's reflection. This is a reflection, and what it's reflecting off of is not water.
Yes. So this is the time for art class. Okay. So when you go to art class, you learn about something called Fresnel. Spelled Fresnel, but pronounced Fresnel because it's French and frou-frou. It's named after a dude. There's also a diffraction named after him. Now, when you have a room and the walls are red and you draw objects within the room and you want to be a good painter, you must add red to the objects. Why? The answer is because the red light is hitting the object and it's reflecting off the object. But the majority of the color you see is from the object. So I might have a white table or a brown table. I'll add some red. Now, the thing is, when you're in a room, you're generally seeing things at certain angles. Now, when you get far enough away from the object's color, let's say the table is blue. You get far enough away from the blue table at a certain angle, the light from the table being blue, the angles that it propagates will be overtaken by the reflected angles of the Fresnel effect. And you will see the table as red instead of blue, even though it's a blue table. Now, it just so happens that these extreme angles, for some coincidence, occur when you're at a very low angle to an object at a great distance, because that's how you get the most acute angles possible, to where the propagation angles and the reception angles and the reflection angles are at such extremes that one overtakes the other. It's very coincidental that it seems to always happen like that. In other words, at certain angles, all surfaces, including water vapor or humid air or different whatever that's particulates in the air, are reflective. And that's what you see, reflections, rather than the color of the thing itself, or rather than color passing through it from something behind it. So no, it's not as simple as I can't see the bottom of something, and I can't possibly think of any other reason, therefore it must be obstructed. Oh, and by the way, I proved this because I can't see the bottom of it. As our friend so eloquently explained to you, that circular logic and proves nothing.
And in case you missed that example, I'm Dutch, so maybe my pronunciation, which is incredibly shitty. I posted in a live stream voice text basically both arguments very simply, and it's doing the exact same thing. You're making an observation, you're reaching a conclusion, and your evidence for that is the observation. That is circular logic by definition.
Hey, gentlemen, it's been a pleasure, but it is 4 o'clock here, and I need to take off.
Okay, man. Hopefully your arms don't get tired.
Yeah, thank you.
All right. Good talking to you, Jesse.
Indeed, thank you, sir.
You're a good sport.
Thank you.
Now when you're going to leave, we're going to talk shit about you.
Sounds like a grand plan.
You can listen to the recording.
Who gets to go first?
Well, I want to caveat his logic string. So if he changed his logic string from the evidence is the observation, he might, try to beef it up a little bit and be like, I can't see the bottom of something. I'm going to assume that that's because it's physically obstructed, right? So he'll do something like this. I can't see the bottom of something. The only thing that can cause the bottom of something to be unseen is physical obstruction. Therefore, it's physically obstructed. Now, the problem is he has to prove all his premises that relied upon in the string. So it can only possibly be caused by physical obstruction. He has to prove that in order for his conclusion to carry. Removing that proof and just appealing back to the observation would be circular reasoning. Not proving that premise that I added would just be insufficient logic. So now let the shit talking fest commence.
Well, I had fun. I really enjoyed the conversation, guys. It was good to listen to. I told him most of those things from a different perspective and different words, but I think it was very well laid out here. So I got nothing to add.
So I just did a little measurement of his his pictures here. So if you measure from the top of the building that's in the center to that white thing, I'm assuming is like a water tower on the mountain. If you measure in one image versus the other image, they're not the same number of pixels distance. I mean, it's not large difference. It's like 8 pixels. So that means in the top one, there's 8 extra pixels just. Why would there be 8 extra pixels from a higher viewpoint? I could probably go across this image all over the place and do the same thing. But if you look at the top one versus the bottom one looks compressed versus the other. The mountain, if you look at the mountain itself, the mountain just looks compressed. That's why I measured from the top of the building and not using the horizon. Because it shouldn't make any difference, right? If you're measuring from 2 visible things. Let me see here. 111. Yeah. It's like a 7 pixel difference, which is, less than 10%. It's like 8%, 7% difference in vertical.
He's working. I'm gonna say.
Yeah. I tried to explain it to him, so you tried to explain that tree thing or the boat thing, Trace? Oh,
sorry, what?
You tried to explain the mirage thing to him?
Oh yeah, I tried to explain everything to him multiple ways. He would always come back with yeah, I don't understand, but what about this? And I'd be like, yeah, okay, I'll explain this.
Do you think he actually doesn't understand, or he's just pretending?
No, I think I'm pretty sure it's narcissism, covert narcissism, or some form of. I thought he was just a compensatory narcissist, and I said as much, and he was like, "Yeah, that's good." Yeah. He took he accepted that, but I think he's more covert based on his actual behaviors. He likes to bury his feelings down and not like. That's why like he doesn't respond to most of the things we're saying. He retreats into himself and responds in his own head, and then just comes out with something completely different because he's not actually listening very well.
It also sounded to me like he was doing, because he's kind of like letting these pauses happen before he answers. Like he's being very, very, very careful about the words he uses, or he's trying to be at least.
Yeah, he's keeping his mask up. It's a common thing you see with him. It's also he comes here for his narcissistic supply and his narcissistic abuse. So like he gets a kick out of feeling like he's winning the debate, and that's why like he comes again with the same thing over and over again. It's his silver bullet, his angles. Ooh, he observes angles, and therefore the Earth is a globe. And so the evidence for that is he observes angles. He just does circular reasoning nonstop.
Angles between two curved lines, right? Because his level is curved and his line of sight is curved. Right. So
yeah, but we already got him to concede and reduce. What he's actually doing is just taking, at best, angles of reception
relative to Plum. In actuality, that's what it is. Relative to Plum, measured at that point, the light came in at this angle from this particular feature of the object in question.
Right, and in a world with curvilinear, omnidirectional, heat-seeking laser beam light, right? You can't then say, "Oh, therefore, object in the distance is at this physical location relative to me." Be ludicrous.
So here's a question: Why don't they just have the angles, like the graded angles, just like right in the optic of the theodolite? Why not just put them right in the optic? You know, like mil dot sights, right? You just put it right on the optic.
Yeah.
Like, okay, that object is 1,000 feet away. Okay, it's at this dot on my optic. Then I know this angular size is this. Or I know it's at this angle above the horizon. Now, obviously, that isn't going to be like super high precision. But like,
right,
you could use it to augment like whatever you're doing.
Right, that's one of the critiques that I gave him. Is like when you have a device like that auto levels. Okay, the accuracy of the auto level is only relevant to it sitting stationary in level. So as soon as you try to track it to an optically designated target that you're choosing yourself via an optical interface that relies on a scope, right? Like let's say an eye scope. Now there may be some with a digital screen, and I mean that might be a little more accurate, but if yours has an eye scope, man, you better hope that your sight picture is perfect before you start to make any claims about what angle you're actually getting to the object you're looking at. Not to mention that we've already agreed that you're only getting angles to intercept angles, not the actual object. So it's not like you're shooting a straight ray laser or a straight, like an ideal ray, like a ray gun ray, to the mountain, and then it's pinging back in a direct linear fashion to tell you that no, the angle that your theodolite is at is directly pointing at the apex of the mountain. No, that's not what's happening. All you're doing is pointing at the angle of reception of the light that appears to you to be the apex of the mountain at your local observation point relative to your local plumb, which your device leveled itself off of originally and then got the off angles from that. That's all you're doing at the end of the day. Then you have to take that and shove it in a matrix of assumptions.
Yeah, I never got to the tilt either. Sucks. I mean, I did it. Like, I keep forgetting that. Like, because I'm still on even to myself. I guess 2017. Well, like people used to say, "Oh, Chicago skyline, why aren't any of the buildings tilted?" Because the tilt would be too small to be perceptible. But that's at that distance. Now we have like long observations. So at 100 miles, it's like 1.5 degrees. It should be tilted away from you. It's easy to see 1.5 degrees. It's not even a challenge. Even someone would that was probably eyesight impaired could see 1.5 degrees.
Oh yeah, well that's their big claim about this whole 900 miles for 1 degree, right? Because you see the sun, like within 1 to 2 degrees off from where it should be. And that was their whole need for terrestrial refraction in the first place.
Yeah. Like, oh, damn. Well, the thing is that, like, if I take a stick and I'm looking at it perpendicular, and if I tilt it away from me, its angular size is going to change. That's why I was like asking. He's like I said, his data is so-called data. It's too clean, way too clean. He's like, "Oh, this all matches perfectly." Well, if it matches perfectly, it has to be cherry picked because there's no other way. If and buts about it, because all the distances vary so much. Each distance, especially like when the distance is like, so a 6 mile difference is going to have different variables to consider than a 10 mile distance versus a 70 mile distance versus a 100 mile distance. Right? You need to keep adding. The longer the distance, you have to like add variables, add uncertainties. And when you then when you take all these numbers together, and then you throw them into a freaking line graph and say it matches the curvature of the Earth, even though they're different distances with different variables and different uncertainties. You have to be cherry picking the data. You can't have different random probabilities added to freaking things, right? Or different biases, right? And then add them all together and have them like even out to match the globe. Like, how would that happen?
You know what one I've never heard any of them reply about in the whole years that we've been doing this is near field and far field diffraction and the consequences that has on your angular resolution and approach angles based on like the propagation angles from the target as they get further away. Because like if you remember that graph, it's not really a graph, but it kind of is. So those two parabolas that Walter Lewin demonstrates how the diffraction actually snaps and accelerates as it gets towards a smaller degree. So cumulatively, diffraction and the available light and the angles, sort of the way, you could correct me if I'm wrong, but I generally describe it as, exponential and hyperbolic simultaneously. And they overtake each other at a certain range, and then you get the snap.
Then there can be diffraction inside the optic too. There is a type of diffraction that happens inside because like it depends on how far the sensor is from the lens objective. Because the light that comes in, like say at the edges of, so say you have the uppermost top part of the lens, the objective lens, and the lowermost part, there's a separation there. And those rays will interfere with each other inside the camera and cause a diffraction. They call it the Fresnel distance or something like that. Like if the distance to the sensor to the objective is too far, you can't use the ray model anymore because those rays interfere with each other. Yeah, I mean, you won't hear Glober say a lot of stuff. They don't ever want to get into the details. They like the what do you call it? The Ronald McDonald version of the globe, where it's just like simple, makes great Discovery Channel documentaries, funds Neil deGrasse Tyson and Bill Nye's lifestyle.
Yep.
I'll take a watermelon and a little toy boat, and this is how the Earth's a globe.
I want to look at that triangle, but I can't know his angular resolution of his optic that he used because he didn't put it in the information box.
He doesn't know. I mean, you'd have to actually test that in practice, though. I mean, you could go by the formula, but we know that no optic actually can reach the Rayleigh criterion. So, like, you can't. You actually have to go test it. And then, depending on the sensors, some might have a better angular resolution for lines than dots, right? Because of the sensor geometry.
So, well, if we know that the available angles consume 6 feet at 3.5 miles roughly for a 6 foot tall man with the human eye of about 1 arc minute, it's not unreasonable that 50 feet would be consumed at 21 miles.
No, it's not.
In line with all those other factors that actually reduce it to be less than 50 feet.
Well, yeah, because of the air. You got to think of the air, even though it's fairly transparent. It's transparent for like practical purposes, right? But it's really not that transparent. It's not like looking through a piece of glass, a manufactured glass, or, a lens. But it is a lens, right? So you are looking through a transparent material with lots of defects in it. And those defects are constantly, they're dynamic defects.
Oh, yeah. Yeah, there's plenty of times that I've been on this mountain over here looking up at what appears to be a clear blue sky, right? And I will see the sun come over my head and start to go towards the airport down the way. And then there's a mountain range before you get to New York, and it's, about 10 to 12 miles, which is about the point where things start turning blue and gray. But before the sun even goes that far, or at least it appears to me to go that far, the entire sun circle will disappear and I won't be able to see the sun, even though it looks like a clear sky. Because there's so much, ambient moisture or particulates or whatever. So it doesn't look gray or cloudy, but it's blue, but I can see the whole sun disappear. It's not strong enough to penetrate.
Yeah, I've seen that lots of times where there's too much stuff in the air and it makes the sun. It's like using like a diffusion filter on a light source, but you don't even have it's so diffuse that you can't actually even make out the sun. It's just kind of like a brightly lit blur in that section of the sky. I just love when they say refraction is just typical. It's always just happening. Then when you start shoveling into that detail, right? Let's drill down. Let's drill down into that. All of a sudden, everyone becomes every glober just becomes I don't know. I'm not a scientist. I don't know about that. I never heard of this. I never heard of that. They were experts a minute ago. It just claimed refraction just happens all the time. And now when you're asking for details, they're all of a sudden they've become mentally retarded. It just shows the disingenuousness of it is what I'm saying. Anyway, go ahead, sorry.
Yeah, his point was generally why can't I see the bottom of something? It must be because it's physically obstructed. And of course, then the counter-argument would be, well, why can I see things I shouldn't see the bottom of? Well, of course, that's just refraction. And I told him, the observations that I do at the small lake, it's the thing disappears bottom up, the thing disappears top and bottom to the center, the thing disappears top down, depending on the day. What's causing that? Well, according to you, it must be obstruction. Well, then he'd say, well, no, obviously it's not obstruction when it's the top down. What could possibly be obstructing it? And then I would say, well, then why is it disappearing, retard? You just told me that the only reason things disappear is from obstruction, and then you told me it can't be obstruction. So what's making it disappear? Well, then the concession would be, well, optical effects. And I say, yes, now apply them to all three categories. Problem solved.
You don't even
because rest assured, if you say, no, the bottom part is obstruction, I'll be like, okay, where's the obstruction? Well, if I apply the globe earth math, I realize that the obstruction is actually less than 0.01 of an inch, and therefore it couldn't possibly preclude an entire boat on the other side of a 300-meter lake, so it can't possibly be physical obstruction. So we were relegated to optics, which, of course, is already known. What you see is created by optical effects. No duh.
Yeah, that's the funny thing is I don't know how many times I've shown the Globers when they do the ships over the horizon can only be obstruction. I show them the RC boat stuff and they're like, well, that's refraction or it's a mirage or whatever. Like, okay, so welcome to flat Earth, man. 5 minutes ago, you were saying that it can only happen from a physical obstruction of water or freaking land, and now you're saying here's another way it's caused by something else. You just conceded. Like, they don't even realize that they're conceding their point. So the air. So we have to get this straight, though. The Glober claim is things that are obstructed by physical ball edge. Things that are not obstructed are caused by unobstructing atmospheric effects. Flat Earthers say, we see too far, and the Globers say that's because of the atmosphere unobstructs objects. And the Flat Earthers say, no, the atmosphere causes obstructions, not unobstructions. Which sounds more reasonable? The air unobstructs things, or the air obstructs things? Which sounds more reasonable to just anybody that's lived a life?
Well,
no one walks around and like, man, thank God for that weather condition. I could see that burglar breaking into the window behind my house.
Yeah.
I caught him this time. He'll never try to break into my house in the middle of a hot summer day again.
Oh, yeah, and by the way, artist perspective, which is often used as practical perspective in reality, which is false, because artist perspective is an ideal model, which assumes straight rays, right, which don't exist in principle. So there's another type of perspective that artists use called atmospheric perspective, where they add occlusion by color fields to things to make them appear to be less resolvable in the distance, adding blue and gray. Exactly as we experience in real life, just as I explained earlier about the sun, and it also happens at lower altitudes, where you're looking out and a haze obstructs the ability to see beyond it, and that haze is basically air full of particulates or water vapor.
Yeah, or both. I also found that wind will like obstruct things. I don't know how it does it, but I know like on a very windy day, you just can't see as far. I mean, maybe that's because the wind is in your eyes. I don't know. But it just seems like the air itself, like, even if it's a clear day, so here it's been pretty clear, but it's been a constant 20-mile-an-hour wind. And like, everything looks clear, but if you try to focus on anything that's like maybe like more than like half a mile away, it looks kind of blurry. Doesn't look clear.
I think it's the turbulence. Like when you are looking over a fire and you see all the hot air rising over the fire and the turbulence in the air there, it distorts everything behind it and makes it much harder to see.
Yeah. Yes, certainly. I mean, there's obviously
that's only a single let's just call it a single point, for lack of a better term, of disturbance, whereas in a wind field you'd have cumulative disturbance over miles even.
Yeah, but there's also not the factor of the heating of the air, so that disturbance wouldn't be as great. Or as obvious.
Dude, the flat earthers, man, they're talking about all these optical effects. Their shit's all fucked up and it's all tarded.
Yeah, it's funny though, but all of a sudden when you like switch to astronomy, and they're like, "Oh, we're trying to minimize scintillation." And anyway, okay, what's scintillation? Well, the air's moving around, and it's hard to get the star to not jump around and dance around. So we can't really see it that clearly and know like where it is. So we're gonna make observations during particular optimum viewing times, where we're gonna put a telescope that has these they call it seeing or whatever. It's like a term of art for astronomy. So they stick their telescopes where there's quote unquote good seeing. It means they have the weather conditions most consistently. Air's not moving, air's not turbulent, has a pretty good, like thermal gradient. It isn't rapidly changing temperatures, Like it's good enough for them, but it's not good enough for us for some reason. It's just funny to me how Globers abandon their principles if abandoning them helps them go anti-flat Earth. Like they just throw it all out the window.
Yeah, I think it's also compartmentalized that most of the Globers don't know like their ass from their hand, so they don't know anything. They're just. I have this vague idea that like my ass is connected to my hand somehow, so I'm just gonna work off of that.
I might not know my ass, but I do know my hand.
Confucius say, "Man who go to bed with itchy bum wake up with stinky finger."
So what's the debate today?
There is no debate. How do you debate objective reality?
No, but I'm saying, what are we talking about today is what I meant.
Oh, we were talking to someone named Jesse Gordon. He got busy, or I don't know. Parole officer showed up. I don't know what happened to him.
Yeah, I just wanted to know what was the topic of today.
Topic today is flat Earth. Topic
awesome.
Every day.
I got my girl listening here, and she's wondering, like,
how long you been listening?
About like 5 minutes.
Oh shit! Okay.
I got my girl here.
That means I have to repeat myself. Anyway, no.
I'll sum up the past 4 hours for you, though.
She was saying something like, "I've taken a flight before, so I could see like the horizon and the curvature." I was like, let's see what they say. I want to describe it better.
So your girlfriend's a tiny earther. Has she ever read the book The Little Prince that lives on a tiny little planet? The Little Prince, it's a book, it's a child's book where the little prince lives on a tiny little planet.
Tiny little planet. I've heard of that book. Like a children's book, right?
So an airplane is nowhere near high enough to see a curved horizon. It's not even close. So say you had a 6-foot beach ball, right? How high would an airplane be off the surface of that beach ball?
I'm telling her right now.
6 foot diameter. Just ask her. 6 foot diameter beach ball. That means, like, if you're a 6 foot man, the beach ball is as tall as you. How high is an airplane off that ball?
Can't think of it.
Just take a guess.
Hey, say the question again so she can hear it.
Okay. Now we're gonna rescale the Earth. The Earth is supposed to be 8,000 miles roughly in diameter. Now, if we rescaled that so that the Earth is a 6-foot beach ball, a beach ball that's 6 feet tall, how high would an airplane be off of it, off the surface of that beach ball? How high above it?
He doesn't know.
one thousandth of an inch. 1/100th of an inch, sorry. 1/100th of an inch. 0.01. Do you think if you had a tiny little camera and you were 1/100th of an inch above a 6-foot beach ball, you could see curvature from that height?
You're saying basically the distance of the plane being in the sky, you wouldn't be able to see curvature.
You're not high enough.
You're not high enough.
Yeah, it's 6 miles above a ball that's 8,000 miles in diameter. You're less than a thousandth of the diameter above the surface. You're not high enough. Nowhere near high enough. And just if you use just plain logic, right? If I looked out the left side of a plane and I saw a curved arc on a horizon, and then I go to the other side of the plane, the right side of the plane. So first I looked out the left, saw a curved horizon out my window. And I go to the right side of the plane and I look out that window. And I see a curved arc of a horizon out that window. What shape does that make? Complete the circle. That would be a cylinder. So no, you never saw a curve from an airplane. Sorry.
Yeah, so we could also get a little more technical. So in order to be able to see a curve, you have to have differentiation in the axes that are available to your vision, X, Y, Z. So if you have a sphere and you're at a point above the sphere to where your field of view is such that it intersects the horizon at a
at the bottom.
Because it's further away from its source.
Rubbish.
Wait, what?
He said, I'll translate, nuh-uh.
Nuh-uh. Powerful argument.
There's going to be a lot of nuh-uhs going on soon, and it's not going to be from me.
Shut up. You're dumb. You're probably the dumbest person in here.
Tell us why the Earth is flat.
Demonstrably.
Tell us how did you discover that the Earth is flat?
Don't speak to me.
I woke up and I walked out of the house and it was flat.
And you think just by looking at it, knowing that, given that the size of the Earth, that you just think it's automatically flat?
Why should I think otherwise?
Are there any reasons why you could be wrong?
Why should I think otherwise?
Answer my question. Are there any reasons that you could be wrong?
Yeah. Yes, exactly. Right? There could be wrong, but we start with that axiom, right?
Yep. So
and what we see is what we get.
Looks flat to you.
It looks flat to everyone.
Therefore,
everyone. So that's a rationalization. So you're using like a rationalization. It could be flat. This experience could be real, but there's reasons why it couldn't be. So, that's your rationalization. So bring some like meat to that bone.
That's good. We're getting somewhere. Could be flat.
Could be. On first impression, that's what it is.
Excellent. So let's drop this is flat business, all right?
Well, I mean, we verified it after that. You said, where did you get the idea in the first place? And I gave it to you.
What did you do?
Well, there's been laser tests. There's been measurements. There's,
really?
Those sorts of things. Yes, really.
What controls did you do for the refraction?
How would you control for that?
I'm asking you the question.
What controls were they done? Well, they did a horizontal pan. They did horizontal panning, and they also did vertical tilting of it to see and to measure how much the angle at the other end changed.
Garbage.
Oh. Okay, so Mike Kavanaugh actually gave an interview about this with Nathan Oakley where he described the entire experiment. Have you ever watched it? You ever heard what he said? Mike Kavanaugh actually had more degrees than you got.
I've watched that garbage show many times, and it's all rubbish.
Listen, this was just an interview. This wasn't like his show. It's an interview he did.
What else have you?
No, you could email them and ask them. They are a public nonprofit.
All right, let's take it from here. So let's talk about your flat Earth. Is the North Pole in the center?
Maybe.
What do you mean,
North
maybe?
Pole? What do you mean by North Pole?
How much time do you need to work it out?
I don't know. What do you mean by North Pole? Even within your model, there are several. Geographic, magnetic. Which one are you talking about?
Let's talk about magnetic West Pole.
Yeah.
Hey, why is Phil telling us to look into? Why is he telling us to ask about flat Earth? Why aren't we asking about the globe right now?
Because I want to know about flat Earth. That's why.
Phil, you don't know about the measurable curvature of the globe.
I want to know about flat
asking
Earth.
any questions about flat Earth right now.
I gave you one. Your response.
I'll ask whatever questions I like. Now you just tell me
You need
what
to
makes
direct
you
those
think the
questions
Earth is
to the
flat.
globe. The globe
You're the
is
one
in
who thinks
question
the
right
Earth
now.
is flat. Explain why you think the Earth is flat.
I just told you, and you're not on it.
No, Phil. I'm sorry, Phil. No,
Got a couple
you're
of
not going to
maybes.
come in here and ask questions about flat. You need to figure out if the Earth is a
I'll
globe.
come in here and I'll ask whatever questions I like.
Stop talking, Phil. You need to ask questions about the globe first. Is there any measurable curvature found on this globe of the one that makes the positive claim that there's measurable curvature? Where is this measurable curvature at? We don't have any.
I want to know about why you think.
No, you don't want to know. You need to know about the globe first. Establish if the globe is the actual paradigm, and then you
That
can
has
ask
nothing
questions
to do
about
with
flat
whether
Earth.
the Earth is flat or not.
You need to
tell
ask
That's what he's trying to get to. Sorry, Miggy, you're very quiet in the background.
You
But
must have an idea.
Professor Phil.
Yeah, I just
you're
told
asking
you
a
why.
question. Yeah, you've asked a question, you've been told why, and Miggy's also trying to tell you why.
And how does the North Pole's existence, non-existence, would ever demonstrate the profile of the Earth? What does that got to do with it?
I'm trying to work out how you think the Earth.
What does the pole have to do with a curving surface?
I'm trying to establish what does the Earth look like in your.
And I'm trying to figure out how that just isn't a red herring, and how you jumped up the laser measurement to the North Pole, which has nothing to do with curvature.
I've already established that you think the Earth is flat because some laser experiment that
laser that was actually 7. They were done in 2 different locations. 2 at one location was 3 weeks apart. They took meteorological conditions. They panned the laser from left to right from a reference target through 3 other targets. Do you even know any details of the actual test? Or are you just not eyeing it with complete ignorance?
I have watched several of these things. Yes.
No, it's not a video. It's actually a report that's in PDF form.
He watched it though.
I watched some late that was done on Jeranism's show or something like that.
I don't know where Jeranism does or doesn't do.
All right. So apart from what's your problem?
Now, just tell me about Antarctica. What's that like?
No. Never been there. Never been there. So we're not going to talk about a place I've never been to. I want to know what your problem with laser transit is.
Australia?
No. But I want to know what your problem, because you're just hand waving it away and not addressing it, and you're just going to talk through me.
Have you not? You've said you've not been to Australia, but can you talk about Australia even though you've not been there?
I'd have to probably speak to an Australian and get some better information.
Yeah. What the hell is this?
I don't know. Some kind of sophistry, man. It's a lot of bollocks.
Is this some type of Elmer Fudd sophistry about you ask people where they've been and you want to go there, and why don't we talk about some place you haven't been? What is your scientific evidence for your spinning ball space monkey religion?
We're not talking about the ball. We're talking about.
Oh, we're not. We better not, because you don't have any.
So,
yes, there's plenty of evidence that the Earth is spherical. The fuck? I want to know what evidence there is that the Earth is flat.
Well, wait a minute. Isn't the Earth observably flat? And even Neil deGrasse Tyson says it. So is it depending on you to prove that it's not flat?
Let me just have a look and see if I can't dump an image for you to have a look at.
God, here we go.
So, check this out. We established that the Earth is flat as a logical axiom because it's self-evident that that's what it is. Okay, the evidence to the contrary needs to be provided. So you can keep saying, what's the evidence for the flat Earth? The evidence is just the first impression of what we experience. Now it's up to you to show evidence that our experience is somehow false.
There's plenty of evidence that the Earth is definitely not flat.
Right, let's have it one by one. Let's go.
Oh, for instance, ships going over the horizon.
Hold tight. Sorry, that's a claim to physical geometric location. Hold on. That's a claim to physical geometric location, as in physical horizon, for things to hide behind physically. The horizon's demonstrated to not be physical and apparent, so therefore can't be physically hiding things and can't be used as measurements to base any geometry on.
It was complete word salad. Rubbish.
How did you account for refraction?
Pardon?
That was complete rubbish.
What part of that was rubbish? Slowly.
You don't like salad.
Okay. Which part of that was rubbish? Which part specifically?
Please explain to me how it is that the ships go over the horizon bottom first.
Can be for a number of reasons, but your claim is physicality of the horizon, which it isn't. It's apparent.
Wrong.
How did he account for refraction? And
Laughing won't help you.
Listen, I'm laughing because this is an honest joke. So if we show ships go over the horizon where it can't possibly be the horizon that the globe says it is at some shorter distance, then what's the reason for that?
It could be all sorts of reasons why you see the horizon in a different place.
No, I'm talking about you see the horizon obstructing a boat bottom first, and as it gets further away, eventually you don't see it. If you see that on some shorter distance than what the globe predicts, so say the globe predicts 2,500 feet, the horizon is, and you see the boat disappearing, but instead of that, you see that happen 5 times closer at 500 feet. What is the mechanism for that?
It won't happen.
Okay.
Wow.
Let me direct your attention to live stream voice text.
That was dope.
No,
this is recorded, right?
Yes, always.
Yeah.
So I'm going to show you a better. That's just a GIF, but I'll show you a better video I got. So there's a lady named Sky Free. Well, I mean, it's 30 seconds. You don't have to review it now. So the GIF actually just shows it. It's in a. I don't know why that's not happening to me.
I can't see what you're talking about.
Okay, there's an animated GIF in the live stream, so it's color corrected to increase the contrast. So this is a camera height of 2 inches. The globe predicts the horizon from 2 inches is 2,500 feet away. This lake is only 600 feet long, and this boat completely disappears beyond the horizon. But the horizon, it's not at the horizon yet on the globe, so how does it disappearing?
Let me show you an example.
And I showed it full color. This girl, Sky Free, and her boyfriend have replicated this about 20 times on a couple different lakes. They've had boats with flags, boats with lights on it, just lights, a bunch of different combinations, and they can just get these little RC boats to just vanish into thin air. Somehow. But this lake is only 600 feet long.
Let me show you.
So we know why this happens, right? This is called total internal reflection.
No, it's got nothing to do with the curvature of the Earth.
No shit. Really?
That's the point. You realize he just showed you the thing you said.
Let's just
won't happen, right?
Let's
hey, Phil, buddy boy. You realize he just showed you what you said isn't going to happen, right? Won't happen. He just showed that to you. You have any rebuttal to that?
Yes, I'll show you in a second.
Okay. Let's look at one image of what? This is the physical location of the horizon, and it's physically blocking the bottom of this object that I'm going to show you. This is it. Is it?
Okay. Look at the buildings. Where's the bottom of the buildings?
The same place that boat is.
Where's the boat?
Is it into the diffraction limit? Is it
We're
somewhere
talking
in
about many floors, not a little
We're
boat.
talking about a boat in a little lake that just did what you're showing us the building is doing.
You're not talking about something that might
But
be
many. But you're trying to be cute by saying many floors, right? So all that matters is the subtended angle. So you could say 20 floors, 30 floors, depending on how far the building is beyond this, right? Like so, a 1 meter wave, a 1 meter.
Do you want to explain where the
I'm trying to, but you're talking too much, right? So say this horizon is like 1 kilometer away, right? And the building is 10 kilometers away. A 1 meter wave, 1 kilometer away is going to block 10 meters at the building. So you could say, where's all these floors? It doesn't mean anything.
Right.
Right? So just like my thumb can block the Empire State Building if I hold it in front of my base, doesn't mean anything. You're trying to just mix and match absolute sizes to some some apparent size.
Where's the pedigree information on? Where's the pedigree information?
Yeah, like how far away is the building? Is it high tide, low tide? Is there a tidal bore? I mean, like.
Yeah, we want detail, Mr. Scientist. We want some pedigree information with your photo here, not just here. Look, where's the floors at? Right? Some pedigree information. Observer height, distance to the buildings. Sort in that vein.
And you want to know.
How did you control for refraction?
That's my question. Wait a minute. That's my question. What's sinking? Anybody can tell me what sinking is?
Yes, I know what sinking is.
Yeah, but we're diverting from the question, right?
What is it? What is sinking? Tell me what it is. What is it?
This is where refraction, normally you've got cold air with warm air, but when you get warm air with cold air, you get sinking. Okay.
What is sinking? Now, what is it? If you use to see it, what is it?
What
look
the hell?
This is
word salad.
Okay, have a look at these wind turbines.
That was
No, we're sticking to your buildings.
Rubbish, mate.
I want you to look at the wind turbines.
No, we're sticking with your buildings before we get to the windmills. Why don't you answer his question?
I don't
answer
care
his question. He asked you what sinking was.
I told you what sinking was. This is where refraction seems to appear to sink, right?
Quite simple. Appear to sink behind what?
Now, can you please have a look at the wind turbines?
No. Sink behind what? Sink behind what?
Whatever
do you sink behind?
Whatever you're looking
at. So what am I looking? So if there's a horizon out there, is it sinking behind the horizon?
If the conditions are right, that can happen. Yes.
Okay. Do you have the pedigree information on this photo so we know what the temperature variation of the water, the air? Do you have all that?
Have a look at the wind turbines.
No,
that means
we can
no.
see the image.
That would be a no then, right? Phil?
No, I don't have the specifics.
Okay, thank you.
Oh,
have a look at the wind turbines, please.
okay. What about
Got specs for those?
Yeah.
Where's the
We need
bottom
observer height. We need observer height and distance.
Why is it that the distance to the wind turbines,
What's the distance?
the further away they are, the more they sink?
What distance? What's the observation height? What's going on?
Because shit gets smaller with distance. It's called second grade. Angular size change with distance. So,
sorry, but they're not getting smaller.
Sorry. So they're not getting shit's not getting smaller with distance.
You can see that compared to the ones that are closer, that's not that much smaller.
Oh, there's not that much smaller. Okay,
Stop fooling yourself.
Oh, okay, stop fooling myself. Okay, what is the observer's height here, and how far is the horizon away?
I don't know exactly the distance, but as far as it would be in the
empty plane then.
No, this is empty. You're just what you're doing. You're showing photos and then wrapping your fairy tale story around it with no evidence. With no evidence. What does empirical mean?
Stop fooling yourself.
What does empirical mean?
Calm down, man.
You sound big mad.
What does empirical mean, Mr. Tapping on the whiteboard?
I don't give a damn about that. Now you just tell me
So what you're doing is you're wrapping your fairy tale story around a simple observation, which is basically religion.
I told you there would be a lot of nuh-ahs going on.
Oh, yeah, you're the one that's stating them. Mr. Rubbish.
You also said it wouldn't be you saying it, but that's clearly been proven wrong.
Be a lot of nuh-ah.
Yeah, you've held up. Yeah,
5 of them.
I'm not going to
you've
let
held
you
up.
go.
You've held up swimmingly, my friend.
Turbines.
Hey, Prof. You just provided 2 pictures with no information, which means nothing. So you have provided nothing here so far.
Let's go back to the RC boats. Let's go back to the RC boats. Obviously, RC boats are a lot smaller than those wind turbines. So, yeah, that's why. Yeah,
No, where the bottoms of the wind
Where's that boat?
Where's the bottom of the RC boat? Answer that first. Okay, now make your RC boat a little bit bigger. There's your answer, Professor Phil.
The turbine is huge. They're hundreds of feet high.
Rubbish. Word salad.
Oh, Professor Phil, you really don't look around you very much, do you?
I'm afraid you don't. I think you do.
No. Do you want to explain why? Would you like me to explain why?
Stop for a second.
Would you?
You have decided to join your little cult.
Oh,
and no evidence.
Join us.
I'm trying to just trying to back up what I just said about how you don't look around you.
Now, please explain to me about the. Actually, I've got another one for you to have.
Why are we explaining your photos? Shouldn't you be the one explaining them?
He can't. He wants us to explain them.
Would you would you go up to a complete stranger and then ask them to explain something for that which they have never made a claim for? Are you batshit insane?
You're the one who said the earth is flat.
Are you batshit insane? Yeah, but I'm not here to explain your photos. You are.
Is the earth flat?
You are. You explain your evidence, sir.
Tell me if you think.
Could I just interrupt here? Sorry, Quantum.
Evidence, sir.
One of the things Professor Phil always says, Quantum, is that you never say the Earth is flat. He's just stated that you say the Earth is flat. So which is it, Phil? Does Quantum Eraser say the Earth is flat, or doesn't he?
I've no idea. He's there now. He can say it for himself.
Oh,
you just said it, didn't you?
Well, he can say it for himself. He's there.
Phil, why do we have to explain your evidence? Does that make any sense?
Why don't you just tell us if you think the Earth is flat?
Why should I explain your evidence, counselor? Bailiff!
Why don't you just tell us whether you think the Earth is flat?
Grab him by his short little pee-pee and throw him out on his neck.
Come on. Is the Earth flat or
You're
not?
a numpty dipshit. You, sir, are a numpty dipshit. You're asking us to explain your evidence.
Just tell me whether
is the globe a circle? Is the globe a circle?
That's insane, sir. Sorry. That's why Indio left. He said, fuck this. You're a moron.
Is the Earth flat or not?
Your sister is.
This really the best argument you got, bro? Prof, this is the best argument.
I've got a photo to show you.
You have any measured curvature at all? You got any of that on hand?
Oh yes,
on
plenty
deck?
of that.
Plenty of that.
We're not
Provide us
claiming
with that, please.
We're not claiming.
Because that's the positive claim, right? Is that the Earth is some type of fucking magic water balls flying around in a vacuum, right?
Yeah.
You got evidence for that?
What magic water? I don't know what magic water balls you're talking about.
Magic, bro. Magic.
It's the one you believe you live on.
I'm not a believer in magic.
You're just a believer in balls. How they become balls? Well, that's not your business.
Yeah, yes, I certainly believe that.
How it is a ball and curved, that's none of your business.
You're supposed to be a prof, and you got like low-level globers actually putting up a better argument than you. This is
really
sad.
Yeah, really.
This is embarrassing.
Embarrassing for me.
Two pictures. First of all, you
So what's up, guys? How are you? Hello, how are you guys?
Hello, hello, everybody. Anybody here? Hello. There is no people. Hello.
Hello, people. What's up? Damn, bro. Everyone is deaf here. Fucking wait.
Hey guys. We just signed this.
Bonjour.
Hello, Leo.
Bonjour.
Hello, guys. Hello.